Good afternoon to everyone. Thank you for coming back for this afternoon. This afternoon, we have a great pleasure of having with us David Banks. David is a professor of statistics at Duke University and a fellow of the ASA, IMS, AAAS, is a past editor of the Journal of the American Statistical Association and founding editor of the Statistics and Public Policy. His research areas include agent-based models, adversarial risk analysis, dynamic network, text data, and human rights statistics. David is a world-known statistician and data scientist. It is really a great honor and pleasure that David accept our invitation to share some of his knowledge with us today. From what I could remember, I think the first time I met David was back in 2012 in the International Symposium on Business and Industrial Statistics in Bangkok, in Thailand, if I remember correctly. And since then, we had the chance of meeting many times and being part of several committees. It is always a great pleasure and honor to interact with David and to have some nice discussions. So David, thank you very much for accepting our invitation, and it will be really a great pleasure to listen to you this afternoon. Thank you very much.
Hi, Paolo. It's an honor to speak with you and everybody else here. I'm going to see if I can share my screen again.
It is here already. We have your screen already, David.
Oh, you can see my screen in full?
Yes, not full screen, but we have your PDF.
Oh, okay.
If you do full screen, I think we will see it.
Oh, okay. Yes, I am trying to do the full screen thing.
Maybe you can do Control L.
Control L will also work.
I think sometimes.
I just tried Control L. There's an odd lag in the audio. Is that being a problem for anybody?
I think not. Maybe if you go to View, I think you should have the full screen there.
I'm trying to click on View with what I have, and that's not working either.
So maybe you can stop sharing and share again. That can work.
Okay.
Yes, now we have it. Yes, that's perfect. David, thank you again. The floor is yours, please.
Thank you. Hi, everybody. It's an honor to speak with you all today. I think we will probably only have time to do non-parametric regression, but this is part of a larger short course. So, data science is an area at the interface of statistics, computer science, and mathematics, and different disciplines have contributed different things. Statisticians contributed a large inferential framework, important Bayesian perspectives. We contributed the bootstrap, classification and regression trees, random forests, and the important concepts of sparsity and parsimony. Computer scientists contributed an appetite for big, challenging problems. They pioneered neural networks. They invented boosting. They got to probably approximately correct bounds, pack bounds, before statisticians did, and we really should have done that, but they were first. They developed programming language such as Spark and Hadoop that handled big data, and those are all important contributions. Mathematicians contributed support vector machines, modern optimization, tensor analysis, and maybe topological data analysis. That's a new area. People talk about it a lot. I haven't seen anything yet from TDA that looks like it's actually transformational, but it's early days yet. Data science is exciting because of the range of problems it addresses. If you're talking about statistical latent Dirichlet allocation is one cool area. It's related to topic modeling, and it's also related to statistical genetics, and it's been used to automatically identify themes in the Wikipedia, Pride and Prejudice, or blog posts. And it has connections with natural language processing and sentiment analysis. Dynamic network models are another important area, and that includes grooming interactions among a baboon troop, protein-protein interactions, traffic flows on the internet, stuff like that. Recommender systems are an area that I'm very interested in. They were the heart of a Netflix competition, but they also inform online dating, they inform Pandora, and they are used for Amazon's book recommendations. The Climate Corporation is using support vector machines in order to try to optimize agriculture. So they advise farmers and agribusiness on what to plant and when, given the context of climate change. And finally, precision medicine is an area in which lots of medical records are mined and individual covariates are used to develop personalized treatment regimes. And in general, one sees that there's little general theory because each problem requires a bespoke hand-fit solution. I.J. Good argued for type 2 rationality. Type 1 rationality means that you should make the choice that maximizes your expected utility. Type 2 rationality is what happens with modern data science, and that means you should seek the solution that maximizes expected utility, but your utility function now includes the cost of computing time, computer memory, data acquisition, and the amount of human thinking and effort that is needed to set up the problem. So for that reason, one might aspirationally want to do a fully Bayesian analysis, but Markov chain Monte Carlo can take a long time to run. And so instead, you'll do something short and fast and non-Bayesian, maybe use a bootstrap or something like this. But my view is that type 2 rationality is why the Bayes frequency distinction isn't really mapping nicely onto modern data science. A key concept in data science is parsimony and regularization. One wants to have the simplest possible model that is adequate to one's purpose. And this often implies that the model is parsimonious, which means it contains only a few terms. And this is often achieved by regularization, which forces terms with small coefficients to be zero in a regression, for example. And sparsity is essentially Occam's razor, and it's a key idea for all the inferential paradigms that we'll talk about. And it takes many forms. In fact, I think there's an underlying theory of sparsity that we have yet to really figure out. In regression, one form of sparsity is to say that most of the explanatory variables are irrelevant. So you do aggressive variable selection in order to thin things out. A second type of sparsity is the belief that a non-negative matrix can be approximately factored as a product of two matrices, each of which have low rank. And that's the key for recommender systems and many other types of latent structure. A third example of sparsity is the idea that the weights on a neural network take only a small number of distinct values. That's also called quantization. So if you're fitting a neural network and you have one node that has weight 1.9, another node that has weight 2.0, and a third node that has weight 2.1, it's better in terms of predictive accuracy to force all three of those nodes to have weight equal to 2. And that turns out to be a different kind of regularization. A fourth idea for sparsity is that for an appropriate set of basis elements, such as wavelets or curvelets or treelets, the signal is approximately a linear combination of a very small number of terms. And finally, a fifth form of sparsity is that a small number of latent factors explains most of the observed variation. I'd like to talk for a minute about old school Bayes and new school Bayes. Alan Gelfand is an old school Bayesian. When he analyzes data, he builds a model for the mechanism that generated the data. He places a subjective prior over everything he doesn't know, and then he finds the posterior distribution. And David Dunsum is a new school Bayesian. His prior is that the model is sparse. And this is often the only way to make progress in really complicated problems, but it's a very different way of thinking about things than the old school Bayes. Now, data science tries to find hidden structure in large, high-dimensional data sets. But as the Gelfand-Dunsum distinction suggests, there can be significant variation in the interpretability of the results. Statisticians tend to favor interpretation, whereas computer scientists often prefer black box models with good accuracy and broad applicability. Both have advantages, but I think there's a growing movement that favors interpretation. Interesting structure can arise in regression analysis, discriminant analysis, cluster analysis, or more exotic situations such as multidimensional scaling. And I am going to focus on regression models, which could be used for climate change modeling, forecasting wine prices, estimating the cost of software development. But there are lots of other things that we could talk about. This is an image from Hastie, Tibshirani, and Friedman's The Elements of Statistical Learning. And although it doesn't quite say everything, it does indicate the value of regularization. So the idea is that we have a true data generating mechanism, which is the truth. We get a realization, which may not be exactly on the truth, but is noisily away from it. We're going to shrink the realization and the truth into a model space, which is denoted by this red line. And that red line is going to separate out the full model that we're going to consider from the model space over here where the truth lives. And you'll see that when we project down onto this model space, the distance between the truth and the realization is smaller. And then if we go further and regularize so that we have a restricted model space, for example, we might be forcing all the coefficients that are not significantly different from 0 in a regression to be equal to 0. Well, that's a subset of the space of all linear models. And that restricted model space, when we project onto that, the distance between the realization and the truth gets even smaller. So this schematic is an idea for how shrinkage and regularization can help us. So now we're going to get on to nonparametric regression. Nonparametric regression is a natural way to introduce the main ideas in machine learning and data science. And the core model here is that our response y is equal to some smooth function f of a batch of covariates, so that's a vector x of covariates, plus noise epsilon. So x lives in a p-dimensional space. We're going to assume that the x's are measured without error. We're going to assume that the epsilons of i's are independent and identically distributed with mean 0. And we assume that the variance of the epsilons of I values is some unknown constant sigma. These are standard regression assumptions, and we can easily weaken them. They're not the assumptions that we really care about right now. Those are minor. We are more interested in the assumptions about the class of functions to which the f belongs. One common assumption sort of pioneered by Grace Waba, is to assume that f lies in the Sobolev space. And these are functions that have bounded derivatives. So the first or the second or the third derivative is bounded by some constant. Another assumption is to assume that f has a bounded number of discontinuities. So it can take a few jumps, but not too many. For right now, we're only going to require that f be vaguely smooth. But we do note that there's a problem called the Curse of Dimensionality. And it says that the problem of estimating f becomes vastly harder as p, the dimension of x, increases. The term was coined by Richard Bellman in the context of approximation theory, but it applies very generally to statistical inference. And people have tried to minimize or evade the curse of dimensionality, and machine learning has tried several computer-intensive techniques, and these include things like multivariate adaptive regression splines, classification regression trees, projection pursuit regression, LOS, random forests, and support vector machines. And we'll talk about all of those. So the curse of dimensionality is going to apply to all multivariate analyses that do not impose strong modeling assumptions. For example, they assume that the relationship between x and the expected value of y is linear, or that f belongs to a specified parametric family of curves, like you take the log of x and the log of y and they're linear related. So if we're doing nonlinear regression or linear regression, then the curse of dimensionality is not going to be, well, it'll be a problem, but in a different way. We're consumed with a situation in which we don't know the functional form f, but believe that it belongs in a set of function that has an open ball in Hilbert space. In terms of sample size n and dimension p, the curse of dimensionality has three nearly equivalent descriptions. The first is that for a fixed sample size n, as p increases, the data becomes sparse. A second statement says that as p increases, the number of possible models that you need to consider explodes. And the third statement is that for large p, most data sets are multicollinear, or the nonparametric generalization of multicollinearity, they are concurve. And that turns out to be even worse than multicollinearity. One thing we might imagine is, suppose we have x values that are uniformly distributed in the unit cube in r to the p. So if p equals 1, they're uniformly distributed on the line segment 0, 1. If p is equal to 2, then they're uniformly distributed in the unit square, and so forth. And I might ask, what is the side length L of a subcube that is expected to contain a fixed fraction d of the data? So if I want to know what fraction of the line segment is going to have in expectation 50% of the data, well, the interval between 0 and 1/2 would be perfectly fine. If I am looking at a square, what is the length of the side of the subsquare that's expected to contain 50% of the data? Well, that's going to be 1 over the square root of 2, because the area of the square who's got length 1 over the square root of 2 is going to be 1 over the square root of 2 times 1 over the square root of 2 equals 1/2. That means that we need to have a side length of 1 over root 2 in order to have a subsquare that will capture 50% of the data in expectation. And as this graph shows, the curse of dimensionality means that in order to capture 50% of the data, we're going to have very, very large side lengths. And in order to have very, very large side lengths, that means that in R to the P, space is getting large very, very fast. And that means that locally, we will never have enough information to estimate all the dips and bumps and wiggles in our function f. Everything is just too far apart to have any resolution on the local shape of f. The second statement of the curse of dimensionality implies that the number of possible models explodes. And to illustrate this, suppose we restrict attention to just linear models of degree 2 or fewer. So if we have one explanatory variable, then there are 7 models that we need to consider. The expected value of y is equal to a constant. The expected value of y is equal to beta 1 times x1. The expected value of y is equal to beta 2 times x1 squared. And then the other 4 models that you see there. And often what we would do is fit the last model, the expected value of y is equal to beta naught plus beta 1 times x1 plus beta 2 times x1 squared. And then we would do hypothesis tests to see whether or not those coefficients are significantly different from 0. And we would remove any coefficients that were not. That's going to crash and burn when we move to high dimensions. It turns out that if we have p explanatory variables, then the number of possible linear models of degree 2 or fewer is going to be 2 raised to the 1 plus 2p plus p choose 2 minus 1. And we will never have enough data to identify which of those many, many models is the best one for our situation. We'd be making so many hypothesis tests that our error rates would blow up and we would not be able to make good decisions. To explain the multicollinearity description of the curse of dimensionality, recall that multicollinearity occurs when the explanatory values concentrate on an affine subspace of Rp. So if all the data x1 and x2, the explanatory variables x1 and x2 lie on a straight line, then we can do a good job of estimating the response y along that line. But any rotation of the plane in which y is fit works equally well, provided we hold the line, the projection of the line onto the line, say x1 equals x2, constant. For large p, the number of possible subspaces is enormous. It's going to be 2 to the p minus 2. And so any shift of those will give us an affine subspace. And the probability that a sample size, a fixed size n, concentrates on an affine shift of one of those subspaces is very large. And what that means is, by chance, your training data are all going to lie on an affine subspace. But because RP is really big, if you want to make a future prediction, it's probably not going to lie on that same affine subspace. And so you're in a straight up multicollinearity problem, and your prediction will probably be very, very poor. So in high dimensions, the predictive mean squared error deteriorates very, very fast. Concurvity is the nonparametric analog of multicollinearity, and it occurs when the data concentrate on some smooth manifold within Rp, where smooth refers to the family of functions f that we are considering. Since the number of smooth manifolds is larger than the number of affine shifts, the nonparametric problem of the nonparametric analog of multicollinearity is even worse. And so that's an incredible problem. In the early 1990s, several researchers obtained results that they claimed avoided the curse of dimensionality. We'll talk about Andrew Barron's results in a little bit of detail. The other two are not as pertinent for regression. None of these results were very practical, and they were toy problems that got asymptotic results that made assumptions that are just not realistic for the types of things that statisticians worry about. I've turned off my audio because there's an odd feedback loop. But I'm pausing now to ask if anybody has any questions about what I've said so far.
Hi, David. So far, there are no questions on YouTube. If someone else, I already asked them to write them down, and I can put them here for you. Maybe the delay and the audio feedback could be because you had your YouTube on, you can simply close your YouTube if you have the YouTube.
Thank you very much.
In any of your tabs, you can just close it and we can
There is this
interact
odd
via
delay
StreamYard.
in the audio here.
Maybe it's because of YouTube.
I have to turn off my audio in order to not talk over myself. I'm not quite sure how we can communicate if there's a question that arises. I think what I will do is pause periodically and ask if anybody has posed any questions. I'm going to talk about two tools that are important for regression. One is a tool for assessing model fit, and the other is a tool for assessing uncertainty. And the first one is usually handled by some variation of cross-validation, and the second problem is usually handled by the bootstrap. And I'm at Duke University. We're all Bayesians here, and neither of these tools is Bayesian. However, they are practical and they are often quick to compute. So both cross-validation and bootstrapping are key methodologies in data science. To assess model fit in complex computer-intensive situations, the ideal strategy is to hold out a random portion of the data, fit a model to the rest, and then use the fitted model to predict the response variables for the values in the holdout sample. And that gives you an unbiased estimate of predicted mean squared error, and that is great. But nobody likes to leave data out when it could be used for analysis. Also, we rarely have a situation where we only fit one model. Usually in our world, we are fitting many models and comparing their fits against each other. And if the same holdout sample is always reused, then the comparisons are not independent. And even worse, the model selection process will tend to choose a model that overfits the holdout sample, which is going to make you spuriously optimistic about your predictions, and it will increase your test error, your error on new data. So cross-validation is a procedure that balances the need to use data to select a model and the need to use data to assess prediction. And specifically, let's say tenfold cross-validation works as follows. You randomly divide the sample into 10 portions, 10 buckets. And for the first bucket, we'll hold out that bucket and we'll use buckets 2 through 10 to fit our model, and then we'll predict the held out bucket number 1. And we'll look at the average squared error in our predictions for that holdout bucket. Then we replace bucket 1 and we remove bucket 2. So now we fit our model using the data in buckets 1, 3, 4, 5, up to 10. And now we estimate the holdout bucket 2, look at the predictive mean squared error in that holdout bucket, and save that. And we do that for each of the 10 buckets in turn. Then we average the predicted mean squared error for all 10 buckets, and that's going to be our estimate of the accuracy of our predictive mean squared error when we go back and use all of the data to fit a final model that uses everything. And you can repeat these steps each time a new model is assessed, and that repetition includes a random division of the sample. The choice of V requires judgment. Peter Bickel did a calculation which suggests that tenfold cross-validation is generally a very good, safe choice. It sort of balances the bias in the method against the variance in the method. And so that's what most people do. But some people like leave one out cross-validation. And that's expensive because you have to fit the model in different times. And you calculate, you use all of the data except for one point, and you predict that one holdout point. And you do that for each of the observations in turn. And this method is almost unbiased, but the variance can be large, and clearly it involves a lot of computation. There are other ways that you could pick what the V should be. One might use the error as a function of the size of the training sample, and when the curve levels off, you stop increasing the V that you're using. Cross-validation is not perfect. The process can use a lot of computer time, especially if you're fitting a complex model. But there are some shortcuts that approximate cross-validation. For example, in a regression model where the estimated values have linear dependence on the observed values, then we can often write the estimated y is equal to a hat matrix times y. So for standard linear regression, that's x transpose x inverse, x transpose is h. And we multiply the observed y's to get the predicted y's, and that's great. And it turns out you can show that the model fitted from all the data except for the ith point. The squared difference between the observed y and that estimate without the ith value, squaring that and add it all up and average it, is equal to 1 over n times the sum of yi minus the estimate fit from the full data divided by 1 minus the ith diagonal element of the hat matrix. So we square that up, and that turns out that we only have to fit the model once. We don't have to fit it n times, leaving out the ith observation each time. So when you have that type of structure, that's computationally efficient, but you do need to calculate the H matrix. And that can also be tricky. And so to avoid calculating H sub II, generalized cross-validation estimates the total squared error as, instead of dividing by 1 minus H sub II, you divide by 1 minus the average of the trace. So you're picking, you calculate the trace of H, and then you divide by n, and that's going to estimate H sub II. I'm going to go back and make one more comment about this. Very often when you're doing cross-validation, you wind up with the problem of twins. For example, in pharmaceutical companies, when they find a biologically active molecule, they'll immediately try to study the properties of very similar molecules. They'll add an OH, they'll add a benzene ring, they'll add, they'll make little changes to that biologically active model, and they'll study those. And they put together this large library of molecules, and then they would like to use something like cross-validation to determine whether or not they're able to fit a model that predicts the properties of new molecules that they have not seen yet. And the problem is that those very similar molecules will wind up in, if you randomly assign them to the buckets, you're going to wind up with a very similar model in the training sample to a molecule that's been assigned to one of the buckets, holdout buckets. And so you're going to think you're doing a really good job of predicting the holdout samples because you're training on data that are very, very similar to data that are in the holdout bucket. So instead of randomly assigning the molecules to the buckets, you have to randomly assign families of molecules to the buckets. So everything that was a knockoff of aspirin is going to wind up in the same bucket all the time. And that will prevent you from being overconfident about your predictive accuracy. And Paul, I'm pausing now for a moment to see if there are any questions.
Can you hear me, David?
I can hear you.
So let me first suggest you to close YouTube and only be with us with StreamYard, because I think that's why you have a delay.
Okay. Let me turn off YouTube. That's a good idea. Okay, I've done that.
Can you hear me now?
Now I can hear you. Great.
And
okay.
No delay, right? Okay, now it will work perfectly. So far we still don't have questions on our chat, so I think you can continue.
Okay. I think I need to stop sharing and start sharing again because I lost the
The full screen.
yes.
Yes, we have here. Yes.
Good. All right. The second tool that we need to use for non-parametric regression is the bootstrap, and that's how we set confidence intervals on things. So we're going to let our sample be x1 to xn. We're assuming those are IID with the cumulative distribution function f, and then for univariate data, the empirical cumulative distribution function is just the average of the number of observations in our sample that are less than or equal to lowercase x. And so it's going to take a jump of size 1 over n at each observation in the training sample. And we know that the limit as n goes to infinity of f hat n is equal to the true distribution f that's generating our data. And so this is a cornerstone of much of statistics. And I'm going to note the estimate of a function of f from the sample as theta hat. And theta hat is going to depend upon both the sample and the f, and we'll see that in a minute. But the idea is that that theta might be the population variance or the ratio of the 7th moment to the 12th moment, or any function for which one wants to develop a confidence region. And to set a confidence region, one needs to know how the sampling variation affects the estimator. And the strategy behind the bootstrap is implied by its name. We have our sample x1 to xn that are generated from f, and we calculate our estimate of the parameter we care about, theta hat, from our initial sample. Now I would like to see how far away theta hat is likely to be from theta, the truth. Well, what I can do is I can use my empirical cumulative distribution function to generate one sample of size n, where I draw from f hat n independently. So I'm drawing from my original sample with replacement. And for that first bootstrap sample, I calculate the quantity of interest. I'm going to call that theta hat 1 star. And I can do this repeatedly m times. So if theta hat 1 star and theta hat m star and all the other estimates are the bootstrap estimates, if those are really spread out, if they're very far away from each other, then that tells me that theta hat is probably far away from the true theta. However, if these are all bunched together and have very small variance, then probably theta hat is close to the true theta. And there's quite a lot of theory here that goes on behind this. Since f hat n approaches f, it will turn out we can show that the distribution of theta hat star converges to the distribution of theta hat, and we are interested in that distribution. So we're going to suppose that x1 to xn are IID from this unknown f, and we want to try to find the distribution of a studentized pivot of the data. And here you can see that the distribution of this quantity depends upon the sample, x, as well as the true unknown mean of f. So that's why this functional depends upon both the sample and f. Equivalently, we would like to understand what is the probability under the true value of f that root n times x bar minus mu over s is less than or equal to t for all t in R. So if we could answer that question, that would tell us exactly what we need to know about the distribution of this quantity. Unfortunately, we don't know f, but the bootstrap approximation to this is going to be the probability under f hat n, the empirical cumulative distribution function, that root n times a bootstrap mean minus the sample mean over the bootstrap standard deviation is less than or equal to t for all t in R. So we have access to the second probability, but we don't have access to the first. Before Efron invented the bootstrap, statisticians used the central limit theorem to approximate the distribution of theta hat by a standard normal distribution. And that was great if we were talking about a mean or a proportion or a difference of means or a difference of proportions. But it really doesn't work if we're talking about the median or the ratio of the 7th moment to the 12th moment. Nonetheless, let us see how good is a bootstrap. Is it better than the central limit theorem? And to answer this, we can use an Edgeworth expansion argument that shows that under reasonable technical assumptions, the probability that we would like to know, the probability under the true F that root n times x bar minus mu over s is less than or equal to t, can be written as the cumulative distribution function of a standard normal plus 1 over the square root of n times a Hermite polynomial that depends only upon small moments of f times the density function of the standard normal. And you keep expanding these out in terms like this, where the jth Hermite polynomial depends upon jth and lower moments of f. And you go through, and that's the Edgeworth expansion. And there's an error term here, and basically we're saying that this error gets small faster than h over n, so this is going to get small faster than 1 over the j over 2 root of the sample size. A pivot function is one whose data asymptotically, a pivot is a function whose data does not depend upon the unknown parameters. And for example, if we're in the class of normal distributions, this is the z transformation, and that will ensure that we don't depend upon any unknown parameter. If the class of distributions if we have in the class of distributions for which the first 2 moments are finite, then this functional is going to be an asymptotic pivot, so that as n goes to infinity, it's going to converge to a standard normal distribution, and that's an asymptotic pivot. For functions that are asymptotic pivots with a standard normal distribution, the Edgeworth expansion implies that the probability that theta hat is less than or equal to y is going to be the cumulative distribution function for the standard normal evaluated at y plus the first term in the Edgeworth expansion plus an error rate that is big O of 1 over n. And the bootstrap estimate for this g of y turns out to have this Edgeworth expansion. It's going to be the cumulative distribution function for the standard normal evaluated at y plus 1 over the square root of n times the Hermite polynomial that depends only upon the first moment of f times the standard normal's density function, plus again this big O term for the error. And what this means is that if we look at G star minus the truth, it turns out that because of the Hermite polynomials, this is going to converge at the rate 1 over n. And in contrast, if we were using the standard normal approximation to approximate the truth, well, the difference between that and the standard normal is going to converge at the rate of 1 over the square root of n. So what that tells us is that if you're working with an asymptotic pivot, then your bootstrap is going to converge faster than the central limit theorem approximation. And that absolutely blew statisticians' minds when that came up. So that is a remarkable thing, and it says that the bootstrap for an asymptotic pivot is clearly asymptotically better than a central limit theorem approximation. Now let's consider a function that is not a pivot. And for example, the percentile bootstrap that Efron suggested in his monograph would be this thing. And that is clearly not going to be an asymptotic pivot because its variance is going to depend upon the unknown variance of f. And I won't get down too much in the weeds here, but if we do the Edgeworth expansion game again, it turns out that when the asymptotics sorts out both the bootstrap and the central limit theorem errors have order 1 over square root of n. So what that tells us is that asymptotically, the bootstrap will do as well as the central limit theorem approximation when you do not have an asymptotic pivot. And so basically, it never hurts to bootstrap. It only helps you. So that's the message with regard to bootstrapping. Now I'm going to step back and talk about smoothing. In the context of nonparametric regression, a smoothing algorithm is a summary of the trend in y as a function of the explanatory variables x1 to xp. And the smoother takes the data and returns a function, which is called a smooth. And I'm going to focus first on scatterplot smooths, for which the dimension of the explanatory variables is 1. And these can generalize to p equals 2 or p equals 3, but then the curse of dimensionality rears its head and it makes them impractical. Nonetheless, these simple one-dimensional smooths can be used as building blocks for more sophisticated smoothing algorithms that break down less badly with large p. And we discussed several of the standard smoothers to illustrate the issues and trade-offs. So essentially, a smooth just finds an estimate of f in the nonparametric regression function y is equal to f of x plus epsilon. So we'll have a running example with this function. I generated data from this curve, and I added normal mean zero variance 0.25 noise. And so this is the data that we get to see. And visually, it's very easy to see that there's a smooth curve that's hidden inside this data. And we would like to look at various strategies for estimating that. John Tukey talked about bin smoothing, and here we break the line into discrete disjoint bins. So we have a bin that runs from -1 to 0. We have another bin that runs from 0 to 1, a third bin that runs from 1 to 2, and so forth. And bin smoothing simply averages the y values within each of these bins. And that's the estimate that we get for the red curve that we saw here. So bin smoothing gives us that. We can have moving averages, and moving averages use bins of varying width, but they contain a fixed number of observations. So in some sense, it's sort of the inverse of bin smoothing. Here, we are forcing the bins to have 3 observations per bin, and then we average the y values corresponding to the 3 x values that are close together. And if we do that, we get a somewhat more flexible smoother than the bin width smoothing gave us. We can probably improve over that by using the running line smooth. So now instead of fitting the average of the y's who have 3 nearby x values, I'm going to fit a line to the 3 y values that have nearby x values. And so now we get something that looks very much more like the original hidden curve that we had. But those are all baby steps. Nowadays, we do things that are more sophisticated. Bill Cleveland invented LOS, and LOS extends the running line smooth by using a weighted linear regression inside the variable width bins. So instead of just having variable width bins and fitting a line, what LOS does is it will upweight the linear regression for values of x that are very close to the point at which we want to make a prediction, and it will downweight the regression weights on data that are far away from the point at which we want to make a prediction. And so that's the strategy behind LOS. And if we apply LOS, what we see is that for our sample data, we get something that looks pretty good and pretty smooth. But LOS is going to break down in high dimensional regression, and so that was not the purpose for which LOS was devised. Kernel regression is another approach, and those are much like the moving averages, except that the average is weighted and the bin width is fixed. Kernel smoothers work well, and they are mathematically tractable. The weights in the average depend upon a local kernel, k of x, and that kernel is typically symmetric, continuous, non-negative, and will integrate to 1. So many people will use a Gaussian kernel. The bin width is set by h, which is called the bandwidth. And so if h is small, then we put a lot of weight on nearby observations and almost none on values that are far away. But if the bin width is wide, then that means that the variance of the Gaussian kernel is large. So we're going to let y sub I and x sub I be our training data. And here x is a vector. And I'm going to set the kernel k sub h of x to be 1 over h times k of 1 over h times the vector x. And this is called the Nadaraya-Watson estimate. And it estimates the value f hat of x as the kernel weight times the response divided by a normalizing function. So we are just sort of using the kernel to put more weight on the values of y sub I that are near the point at which we want to make our prediction. So Bernard Silverman showed that for kernel estimation, the Epinetchnikov function has very good properties asymptotically. And so we are going to, so the Epinetchnikov kernel asymptotically has, is sort of the right kernel to use for mean squared error. And so that's what the Epinetchnikov kernel looks like. And if we apply the Epinetchnikov kernel to our data, then we obtain this as our smooth. And probably the bandwidth was a little too small because that curve wiggles around a little bit more than is visually appealing. So if we were redoing this, we'd probably pick a larger h value and smooth a little more widely. The last smoother I want to talk about is spline smoothing. And here we estimate f by minimizing the equation that balances least squares fit with the wiggliness of the function that we estimate. So we want to minimize the sum of squared discrepancies here, but we pay a penalty if the kth derivative of function f is too large. So this is the function that this is the minimization that we're trying to do. And it turns out that if we do this over the space of square integrable functions, then the solutions that one obtains are called the smoothing splines. And smoothing splines are piecewise polynomials, and the pieces are divided at the sample values x. The x values that divide the fit into polynomial portions are called knots, and usually splines are constrained to be smooth across the knots. Regression splines have fixed knots that need not be chosen by the data. So you can pick the knots, and here I've picked the knot to be equal to the integers, -1, 0, 1, and so forth. There's a literature by Pat Smith on knot selection techniques. So if you don't want to pick the knots to be the integers in this example, we could use the data to tell us where the knots should be placed. So there's a way of estimating really good knots. And splines are computationally fast. They enjoy strong theory. They work well, and they're very widely used. So the first order smooth is piecewise linear. So we're restraining the first derivative of the function f. And the second order, if we restrict the second derivative f in size, then it's going to be piecewise quadratic. So here we have a first order spline, here we have a second order spline, and both are fitting the data that I showed you before with knots that occur at the integers. And here we're requiring that the splines be continuous or even differentiable across the knots. Yeah. If you want to compare smoothers, most smoothing methods are approximately kernel smoothers with parameters that correspond to the kernel k of x with bandwidth h. And in practice, you can fit the h by judgment. You can find the optimal h. You can fit h adaptively from the data, or you can try and fit the kernel adaptively. And my sense is that you hit a point of diminishing returns when you fit the H adaptively from the data. That's about as far as anybody would really want to work. That's as hard as anybody would like to work in trying to fit a particular data set. Bernard Silverman has a nice discussion of the issues in the context of density estimation. Leo Breiman and his student, I think it was Mark Peters, gave results on a simulation experiment to compare the smoothers. And basically what they found was that adaptive kernel smoothing is good, and you can do theoretical results there, but it tends to be slow, which is a significant handicap in modern big data applications, especially if you're in high dimensions. Smoothing splines are fast, and they're usually pretty accurate. Some people don't like their tail behavior very much. I think that's not really a concern. And everything else that's been considered is really not competitive in hard problems. So a theoretical understanding of the properties of smoothing depend upon the eigenstructure of the smoothing matrix. And Hasty, Tibshirani, and Friedman, second edition, provide an introduction to this area in chapter 5. In linear regression, one starts with a summary with a quantity of information equal to n degrees of freedom, where n is the number of independent observations in the sample. For each estimated parameter, you're going to lose 1 degree of freedom, and that is because each estimate corresponds to a linear constraint on the n-dimensional space for the data. And smoothing is a nonlinear constraint, and that's going to cost more information. But many smoothers can be expressed as a linear operator, a matrix S, that acts upon the response variable y. And it turns out that the degrees of freedom lost to smoothing can be calculated as the trace of S. So in linear regression, the smoother is the linear operator that acts on the data to produce an estimate. So our estimate is y hat, and here we're obtaining y hat by multiplying S times y. And you recall earlier we talked about the hat matrix H. Well, now we're talking about a smoothing matrix S. And if the smoothing matrix were the linear model smoothing thing, then we get this. And the trace of S is going to be the trace of this. Turns out that you can move things around inside the trace. We wind up getting the trace of I. That's going to be equal to P. And here we're not including the column that corresponds to the intercept. If we did, we would lose the usual additional degree of freedom for estimating the intercept. That means the degrees of freedom associated with linear regression is going to be P or P plus 1 when we include the intercept. But we can also talk about smoothing operators for the bin smoother. And here you can divide a line segment into m equally spaced bins, say B1 up to Bm. And then if there are k sub j observations that lie in the jth bin, then the bin estimate is going to be 1 over k sub j times y sub I times an indicator function for whether or not xi lies in the jth bin. And we can write that as a smoothing matrix times y. Each of the block matrices corresponding to block submatrices corresponding to B1, B2, B3, etc., are a diagonal matrix whose submatrices have every entry equal to 1 over k sub j. And that means if there are k sub j of those subentries, then we're going to lose a degree of freedom for each bin that we have. And so if we have m bins, we're going to wind up losing m degrees of freedom. So that means that that's how many degrees we can calculate how many degrees of freedom we lose in doing bin smoothing. And most of the other smooths, except LOS, can be written in terms of an H matrix. Most smoothers are shrinkage estimators. Mathematically, they pull the weights on the coefficients in the basis expansion for y towards 0. And that's an example of the power of sparsity, as we discussed back on slide 6. Shrinkage is why smoothing has an effective degrees of freedom between P, as in regression, which does not shrink, and N, which is one we would expect from a naive count of the number of parameters needed to make the function perfectly interpolate each data point. For bin smoothing, we can undersmooth or oversmooth. If M is much less than N, then there are few bins, and the fitted function is going to have very few jumps, and it's going to be oversmoothed. But if M is large, then it's going to be using more like N degrees of freedom, and then it's going to be undersmoothed and have a lot of variability in the fitted surface. So this line is an example of oversmoothing. This other line that wiggles around is an example of undersmoothing, and you want to try and strike the balance between those two properties. And in particular, mean squared error is a criterion that balances these against each other. The mean squared error for fitting a smooth function f hat is going to be the expected value of f hat minus the true f squared, integrated over all of the x's, and that's going to be the variance of f hat of x plus the bias squared of f hat of x. So that's how smoothing works. And I suggest that we pause for 5 minutes, take a break, and come back and begin talking about non-parametric regression in more detail. Thank you so much.
David, thank you very much for this first part. It has been quite a very nice sharing of information. My suggestion is that we start the second part with some questions that are in the chat. Is that okay?
Please. Yes.
So I have here a question from Vinod Kumar. I think this question was around your slide 18 to 19. He was asking what are the models of fit, and then he continues how to select the models of fit.
Yeah.
I think you made this question when you were in your slide maybe 18 to 19, I guess.
Yes. Well, I'm showing slides 18 right now. And for example, in doing a regression model, you might decide that you would like to consider models that contain linear and quadratic terms. That would be one family of models that you might consider. Alternatively, you might consider models that are kernel smooth regressions. And so you would be comparing maybe a kernel smoother that uses Epinechnikov kernels to a model, a regression model that uses normal distribution kernels. Or you might be comparing Epinechnikov kernels that have bandwidth h equals to 10 to Epinechnikov kernels that have bandwidth equal to 5. So typically in non-parametric regression, you're going to be trying very many different models to find one that works well. And that will involve variable selection, for example. You might decide to try a model that includes a particular explanatory variable versus one that leaves that explanatory variable out. Is that responsive to the question, do you think?
Yes, I think so. We have a couple of more questions. We have one from, I will try to say your name. I apologize already. So Vyacheslav Lyubshich is saying something like this. When relatively small samples are used in k-fold cross-validation, the number of selected nodes in GAN smoothers is often smaller than that would be selected when re-estimating the model on the whole sample. Would you recommend to force the number of nodes to lower value, as in cross-validation, when re-estimating the model on the whole data?
Yes, if you're dealing with small data sets, then you have a number of challenges. And as you say, the knot selection is going to be an issue. You just won't have very much information on what the good knots are. Cross-validation is going to have too few observations in each bucket to be helpful. And as we sort of saw with the Curse of Dimensionality, if you are in high dimensions and have small samples, my advice is to phone in sick that day. You're not going to be able to get a good answer.
Thanks, David. We have one more question from Alberto Rodriguez. He says, David, the knots of regression splines are pre-specified in the usual approach. Do you think this could be a problem in predicting modeling? Are there methods to solve this problem?
Yes, and you're quite right. The smoothing splines put the knots at the data, and that's not what we really want to do if we're doing regression. Regression splines are splines where you fit the knots at places other than the data. And as I said, Patricia Smith has a paper in which she worked out basically a set of f-tests for deciding where you need to have knots. If the function is wiggling around a lot in a particular region, then you want to have a lot of knots there. If the function is pretty smooth in a region, then you don't need nearly as many knots. And so you adaptively place the knots according to tests for whether or not the knots are explaining useful amounts of variability. Jerry Friedman in one of his papers, I think it might have been the multivariate adaptive regression splines, talks about this at some length.
Yes, thank you very much. Vinod and Vyacheslav, thank for your responses. I also have here a comment from Fabio Molinar saying great lecture, and another one from Rosaria Lombardo for very nice lecture. And that's all that we have for now. When you would like to continue, please just go ahead.
Thank you, Paulo, and thank you to the very gracious audience who say such nice things. I really appreciate it. We're going to start talking about non-parametric regression a little more specifically now. And I remind you that multiple linear regression has been around forever, and it's great. Everything is interpretable. There's a huge amount of theory that support all of the inference, and we know how to make predictions. If we want to include interactions and transformations, that's easy to do. So we can take the log of an explanatory variable if we want to make a transformation, or the sign. I will note that economists seem to think that an interaction has to be the product of, say, x1 times x2. And just want to point out that the world is bigger than that. For example, if you took the minimum of x1 and x2, that would be a perfectly fine transformation to include as well. And in many cases, that's actually a reasonable interaction to consider. We can use dummy variables to include categorical information, and computation is fast. But the additive linear models are too flat, and the class of all possible smooth is too large. And so we're going to try and find a compromise with the class of additive models that is shown here. And the additive model says that our response y is equal to an intercept plus a sum of univariate smooth functions f sub k. And then there's error, of course. And we do not know what the fk smooth functions are, but we're going to estimate those from the data. And the basic assumptions are as before, except now we add that the expected value of f sub k is equal to 0, because otherwise we have identifiability problems. For example, if the expected value of f sub k were 2, then I could simply lower beta naught by 2, and that would all cancel out. So to ensure identifiability, we're going to require that the expected value of the f's are 0. The parameters in this additive model are the functions f sub k, the intercept beta naught, and the unknown sigma squared for the variance of the errors. And in regular linear models, each parameter that we fit costs 1 degree of freedom, but fitting these smooth functions is going to cost more depending upon what kind of univariate smoother we use. And I will note that you can require that some of the fk be linear and monotone. For example, if I were trying to predict how long somebody's going to live from blood pressure, BMI, things like that, and one of the pieces of data I had was how many cigarettes they smoke, well, I would like to have I can force a monotone decline in your life expectancy as the number of cigarettes you smoke increases. It's probably not a linear relationship, but it should be monotonic. We can include a couple of low-dimensional joint smooths. So we might jointly smooth x1 and x2 instead of just smoothing x1 and then smoothing x2 and adding them together. If you want to include interactions, we can do smooths of, say, product interactions. Transformation of the variables is done automatically, so we don't need to worry about taking logs or whatever. It turns out that many of the regression diagnostics, such as Cook's distance, will generalize to the additive model situation. If we have heteroscedasticity, unequal variances that depend upon the explanatory variables x, then we can do basically iterated, reweighted least squares. And that's the way we would handle heteroscedasticity in the linear model, but it also applies to the additive model. We can have deviance tests for comparing nested additive models. And so that will help with variable selection. And we can use the bootstrap to set pointwise confidence bands on the fk. And if those pointwise confidence bands include the 0 function, then it would certainly make sense to just omit that term. However, model selection, overfitting, and multicollinearity remain serious problems, and the final predictive accuracy may still be poor. The way additive models work is through the backfitting algorithm. And this allows one to use an arbitrary smoother, say splines, LASSO kernel, to estimate the F sub k. So as motivation, let's start by assuming the additive model is exactly correct. So there is a sum of functions which, when added to an intercept, predict the expected value of y. And what this implies is that if we fit the additive model with all of the explanatory variables except for the jth explanatory variable, well, we can smooth the residuals with respect to that. And that's going to be the smooth of the residuals corresponding to not fitting x sub j. And the backfitting algorithm iteratively goes through and it leaves out x1, then it leaves out x2, then it leaves out x3, and so forth. And at each stage, it replaces the conditional expectation of the partial residuals with a univariate smooth. And I don't want to belabor the notation here. It turns out that it's convenient to transform the f sub k from being a smooth function to being a vector whose ith entry is equal to f sub k evaluated at the ith observations kth explanatory variable. Don't worry about that very much. So for any z and Rn, I'm going to let s sub z of given x dot k be the smooth of the scatter plot of z against the values of the kth explanatory variable. And in that case, the backfitting algorithm is going to work this way. We start off by setting, say, initial guesses about the intercept beta naught and the fk functions. And typically what you're going to wind up doing is set beta hat is equal to y bar, and we're going to do linear regression on each of the explanatory variables separately. Then we go through and we solve those p equations, leaving out x dot 1, x dot 2, x dot 3 in turn, and we smooth. And then we simply iterate until the changes in the fk between iterations is sufficiently small. So when none of the fk's changed by more than, say, 0.001, then we would stop the process and declare victory. And in principle, you could do all sorts of exotic things like use kernel smoothing for x1 and LASSO smoothing for x2 and spline smoothing for x3, but that doesn't seem to be really a very important feature. It turns out that the estimating equations that are the basis for the backfitting algorithms have this matrix and vector form pf equals q times y. And we can identify what the matrices p and q would be. And it turns out that the iterative solution for this thing is the Gauss-Seidel algorithm for linear systems. And this means that the backfitting algorithm is going to converge for smoothers that correspond to a symmetric smoothing matrix whose eigenvalues all lie in the interior of the interval from 0 to 1. And that's going to include the smoothing splines and most of the kernel smoothers. It doesn't include LASSO. And for an example of a kernel smoother for which it fails, it would be a kernel smoother that puts zero weight. Imagine a bivariate normal distribution. Imagine a bimodal distribution. That would be an example of a case in which the eigenvalues would lie outside of that region. So, so we know that the backfitting algorithm will converge for reasonable classes of smoothers, and if it converges, then the solution is going to be unique unless you have concurvity in your data. And in that case, the solution is going to depend upon what the initial conditions for your algorithm were. Concurvity is going to arise when the x values lie upon a smooth manifold in Rp. And for our examples, a manifold is smooth if the smoother used in the backfitting algorithm can interpolate all of the x values perfectly. So That's what it means for things to be concurve. This is exactly like the non-uniqueness of regression solutions when the X matrix is not full rank. And really what's going on there is pretty direct. If we're doing linear regression, then we have a linear smoother, and if all the points lie on a line, all the explanatory values lie on a line, then we have multicollinearity. And concurvity simply says that if all the X values lie upon a surface that's used by the smoother, then you have concurvity. If P is an operator on P tuples of functions G, and Q is an operator on a function H, then the concurvity space is the null space of PG equals QH. And so it's going to be the set of functions G such that P times G is equal to 0. So in that case, G sub J of X sub J plus the sum of all of the explanatory variables except for the kth one is equal to 0. And I should probably put an intercept in there. I overlooked that. But those are the conditions under which you have concurvity problems. What we're going to do next is generalize the concepts of this additive model to other situations. So the generalized additive model assumes that the response variable comes from an exponential family. And this is like the generalized linear models approach that was developed by Peter McCulloch and John Nelder. And there, what we would do is take a transformation of the responses y that linearize the relationship between the transformed y and the explanatory variables x. So, for example, if y is Bernoulli or binomial, then what we would do is the logit transformation. So we're going to take, instead of dealing with the probability of success given a vector x, we're going to take the logit of that. That's going to be the natural log of the probability of success over 1 minus the probability of success. And that just gives us logistic regression. So now what we're imagining is that our transformed mean response, say the logit, is equal to beta naught plus a sum of smooth univariate functions. And as with generalized linear models, the link function is chosen by the user based upon domain knowledge. Only the relationship to the explanatory variables is modeled. So for the generalized version of logistic regression, it's going to be the logit of P of X is equal to beta naught plus a sum of smooth functions. And the generalized linear models are fit by iterative scoring, which is a form of iteratively reweighted least squares. And that speaks to the fact that if you have binomial data, we know that the variance of the binomial depends upon the value of P. And so, your different areas are going to have different variances. And so you're handling this the way you handle heteroscedasticity. And so the generalized additive model modifies backfitting in a way that's analogous to the iteratively reweighted least squares. A different generalization of the additive model is called projection pursuit regression. And this treats models of the form the response y is equal to beta naught plus the sum from j equals 1 to some number r of smooth functions of a linear combination of the explanatory variables. And so if r is found from the data by, okay, you don't know r in advance. It turns out that if r is very large, then these things get impossible to interpret. But we could estimate r using cross-validation. So we would look at many different models, r equals 1, r equals 2, r equals 3. We compare those using cross-validation and try and find a value of r that gives us a good fit. Jerry Friedman and Werner Stutzler developed projection pursuit regression as an exploratory data analysis strategy to try and find rotations of point clouds that have interesting structure. And projection pursuit regression tends to work when some of the explanatory variables are similar, commensurate. So if we're looking to predict lifespan, similar biometric measurements might be bundled into one linear combination. Education measurements might be bundled together in a second linear combination. And maybe if you have information on income, standard of living, stuff like that, that would be a third linear combination. Picking out a linear combination is equivalent to choosing a one-dimensional projection of X. And for example, if we take beta transpose is equal to 1, 1, and X lies in R2, then beta transpose X is a projection of X onto the subspace that has a set of X's such that X1 is equal to X2. So we're taking an observation here in our data set, and we're projecting it onto this line, X1 equals X2. If R equals 1, then the fitted projection pursuit surface is constant along the lines orthogonal to S. If F1 were the sine function, then the surface would look like corrugated aluminum, but oriented so that the ridges were perpendicular to S. So that's actually probably a useful mental image. If I had a sheet of corrugated aluminum to represent my response, f of x, and I have x1 and x2, and if the x's are, and if the response y is such that the ridges in the corrugated aluminum are aligned with the natural axes, then the additive model will do a great job in predicting that. It will say in one direction that's a sine function, and in the other direction it's a constant. However, if I rotate the corrugated aluminum 45 degrees out of the natural axes, now the additive model will be completely a C. It will fail. But projection pursuit regression would be able to make this this projection, this 45-degree change, and then it can fit the sine function to that rotated surface. So that's the situation in which projection pursuit regression works very nicely. So for R greater than 1, the surface is hard to visualize, and the beta 1s and beta Rs need not be orthogonal. So this is not like principal components analysis or principal components regression. But you're able to prove that as R goes to infinity, projection pursuit regression is a consistent estimator for smooth surfaces. I don't think that that's such an important property, really. I would value a simpler model that we can understand over something that will eventually be consistent in very high as n goes to infinity, as R goes to infinity. The projection pursuit regression algorithm alternately applies backfitting to estimate the f sub j with Gauss-Newton search to estimate the beta j's. So first you estimate the f sub j, then you estimate a new projection, and it alternates back and forth between these. In order to run the algorithm, you have to pick your R first, and as I said earlier, that could be done with cross-validation. So you pick your R, you get initial estimates of f hat j and beta j's, and then you go and you loop through the R fits here, and then you use Gauss-Newton to find beta hat j. And if the maximum change in beta hat j is less than some threshold, then we're going to exit. So that's a pretty straightforward generalization of the backfitting algorithm to handle the case of projection pursuit regression. A third approach uses neural networks. And interestingly, these methods turn out to be very similar to projection pursuit regression. And there are a number of different ways to perturb the neural net strategy, but I'm going to focus on the basic feed-forward network with one hidden layer. Obviously, this is dated. We now all do deep learning, but it's easier to understand what's going on if we have the feed-forward neural network with one hidden layer. This neural network is going to fit a model of the form y is equal to beta naught plus a sum from j equals 1 to r, where r is the number of nodes, of the weight of the nodes times an activation function at that node. And that activation function is going to have a linear combination of the x's plus what the computer scientists call a bias, but which we would call an intercept. And this function, psi, is a sigmoidal function, and all of the other parameters except for the r are going to be estimated from the data. The r comes from the architecture of the neural network. So if you look at this linear combination of the explanatory variables is very much like what projection pursuit regression is doing. And the difference is we are not specifying a sigmoidal function in projection pursuit regression. We're letting the data tell us what is a good, smooth transformation of the linear combination. So neural networks with a single hidden layer are close cousins of projection pursuit regression, and in fact, a little bit more restrictive than PPR. I've said the first part. The parametric assumption allows neural nets to be trained by backpropagation, which is based upon the chain rule for differentiation and makes use of the parametric form of the activation function. So it's similar to backfitting, but it's faster because it does not require this iterative smoothing. And we'll talk later about how Barron showed that neural networks, in a narrow sense, evade the curse of dimensionality in a rather technical and specific result. Here's the notion. A standard way of assessing the performance of a nonparametric regression is in terms of the mean integrated squared error. So the mean integrated squared error of an estimated function g hat is going to be the squared discrepancy between g hat and g integrated over the entire region for the x's, and the x's need not be uniform over that region. They can have some multivariate normal distribution, say. And before Andrew Barron's work, people had thought that the curse of dimensionality implied that for any regression procedure, the mean integrated squared error had to grow faster than linearly in P, where P is the dimension of the data. And Barron showed that neural networks could attain a mean integrated squared error of order big O of 1 over R, the number of hidden nodes, plus big O of R times P over N log N. So that would grow linearly in P. And that was a surprising phenomenon, but when people started to look at the proof, our enthusiasm melted away. It applies to a class of functions G, whose Fourier transforms G tilde satisfy are bounded in this sense. The integral of omega times G tilde of omega d omega is bounded by some C in the complex plane. This class gamma sub C is thick, meaning that it cannot have a finite dimensional parameterization, so it's a truly non-parametric family. It contains an open ball, is another way to think about this. But it excludes important functions such as hyperflats. And we would certainly be able to estimate, we would like our family of estimators to be able to recover a straight line or a hyperplane, and that's not part of the gamma sub C. Furthermore, as P gets large, the measure of gamma sub C within the space of functions goes to 0. So that's also a bit problematic. Nonetheless, it's an interesting proof strategy that Barron had, and his approach was to show that for all G in gamma sub C, there's going to be a neural net approximation G hat star, such that the distance between the true G and G hat star is squared, the norm of that that's squared, is less than some amount. And then he showed that the mean integrated squared error in estimating any of the G hat star functions is bounded. And he combines these two results to show that the distance here is small and the error in estimating G hat star from data is going to be small, and that gives him a neural net bound on the mean integrated squared error that is linear in P. Another generalization of the additive model is called alternating conditional expectations. And ACE seeks transformations of the explanatory variables x1 to xp and the response variable y that maximize the correlation between the transformed y and the sum of the transformed x's. And it turns out that that's equivalent to minimizing this thing, where expectations are taken with respect to the yi and the xi. And the key thing here is that we do not want to have the trivial transformation such that, say, g of y is identically equal to 0 and all of the f sub j's are identically equal to 0. That would maximize the correlation, but that's obviously a pathological solution. By dividing through by the expected value of g squared of y, we prevent that from happening. So ACE is going to modify the additive modeling strategy by allowing arbitrary transformations of the response variable, and it's using maximum correlation instead of squared error for optimization. So ACE was developed by Leo Breiman and Jerry Friedman, and in practice it resembles canonical correlation. So we're going to initialize by picking a transformation G, and usually it's basically a standardization like this. Subtract the mean and divide through by the standard deviation. And we can do linear regressions for the xj's. So we regress x1, x2, x3 against y, and that gives us our initial guesses, f sub j. Then we do backfitting to fit an additive model to the transformed y's to obtain new functions f1 up to fp. Then we do smoothing to estimate the y. We look at the sum of, we look at the fitted model for the p explanatory variables given the y's, and then we smooth the residuals in the y's. And we're going to standardize to get a new g of y by dividing through by the variance of g tilde of y. So that keeps things from going to 0. And then we alternate between steps 2 and 3 until this discrepancy converges to 0. This is going to find the unique optimal solution given the eigenfunctions associated with the largest eigenvalue of a certain operator. And in the JASA paper, they work out what that operator is. And I will note that Rob Cass in the discussion noticed that sometimes the eigenfunctions associated with the second largest eigenvalue of that operator are more interpretable than the eigenfunctions associated with the largest eigenvalue. So if you ever jump in on this, be aware that it might be worth looking at the second largest eigenvalue. For later use, I'm going to be talking about the application for ACE that was described in the Breiman and Friedman paper. Leo Breiman had data on the ozone concentration in the atmosphere over Los Angeles for 330 days of the year. And here's the ozone concentration, and what's plotted is the ACE transformation of the ozone concentration. So you're going to make a transformation G of the response variable, and it's not quite linear, but it looks pretty close. One of the explanatory variables is visibility. And here we see that we have this sort of curvature in the visibility. This is the smooth that was estimated by ACE for determining visibility. Here's the temperature, which is another predictor. Day of the year is a third predictor. And you see that these things tend to look sort of linear or quadratic. And that will become important later on. I actually happened to be doing my postdoc at Berkeley when Leo was working on this paper. And he came into a class I was auditing in which he had the day of the year transformation. And his plot did not look like this. There's a huge notch here, and a huge notch here, total discontinuity in the curve. And one of the clever PhD students at Berkeley noticed that those notches occurred when daylight savings time took place and then stopped. And what was going on became very clear, and Leo was delighted. The auto exhaust in the Los Angeles area had either an extra hour to bake or an hour less to bake on days when before and after the daylight savings change. And I thought that was actually a wonderful proof of concept for this technique, because Leo had not been thinking about daylight savings time at all, but the data made him realize that, and that was and that's what good statistics is supposed to do. Leo decided to not discuss that in the paper. Instead, he used the ozone concentrations from an hour earlier or an hour later, before and after the daylight savings time change. And that gave you the smooth figure that you see there. Two other explanatory variables was inversion at base height, and then he also tried using just the day of the year as the only independent variable. And so that was an early application of ACE to the Los Angeles ozone data. It turned out that 4 of the 8 variables explain 78% of the variation after ACE transformations. And if you use all 8, you only explain 1% more of the variation. But we're going to reuse this example in section 5.5. And that'll be an interesting story when we get to it. From the standpoint of nonparametric regression, ACE has several undesirable features. First off, ACE will generally not find G and F, but rather some function composition H of G and H of F. The solution to ACE is sensitive to the marginal distributions of the explanatory variable. ACE is going to treat the explanatory and response variables in the same way because it's doing correlation, but in regression, we usually treat them asymmetrically. We're assuming that all the error occurs in the Y's. And as I mentioned, Rob Cass pointed out that the second largest eigenvalue can be better. There are other pathologies, and you can see the discussion of the Bryman and Friedman paper to get more details on those. But these pathologies motivated Rob Tibshirani to invent a version of ACE that he calls additivity and variance stabilization. And it addresses many of these undesirable features. And in particular, Rob realized that heteroscedasticity was a common problem that lies at the roots of the issues that ACE has. And it's known that if a family of distributions for Z has mean mu and variance that depends upon mu, then the asymptotic variance stabilizing transformation for Z is going to be this thing here. And the APHIS algorithm runs just like the ACE algorithm, except that in step 3, it does a variance stabilizing transformation before the standardization. So here, it does this, then it adds that variance stabilizing transformation, and then it does the standardization. I just have 2 more variations of nonparametric regression that I want to talk about. One is recursive partitioning regression, and the most famous of those methods is CART, but there are quite a number of CART-like techniques out there. And in regression, CART acts as a smart bin smoother that performs automatic variable selection. So basically, it's fitting, it's looking for regions, R sub j, and for each region, it says that the response y is a constant in that region. So that's very much like the bin smoothing that we discussed first, except CART picks the bins rather than having the bins prescribed by the analyst. And the R sub j are disjoint, and the beta j is the average of the y values within the rj. So the CART model is nice because it produces a decision tree that is helpful in interpreting the results, and that's one of the key reasons why it continues to be popular. So here's the region version of this, And here is the tree form of this. And unfortunately, this graphic uses X and Y, and I would prefer they used X1 and X2, but I think we can get the idea nonetheless. So in this region at the top, the estimated value of that function f of xy is 0. In this region, the estimated value of the function is 2. In this region, it's also 2. In this region, it's 1. And that corresponds to a decision tree that says, is y less than 4? If so, go down here. If not, say that the answer is the estimate of the regression function is equal to 0. Here we ask, is x less than 3? And if x is less than 3, we go down here. Otherwise, we estimate 2 as our response for this function. Then we come here and we ask, is y less than 2? And if so, then we say it's 2. Otherwise, our estimate of the function is going to be equal to 1. So decision trees are nice. CART focuses on a different type of interaction than the usual product term. So it looks for thresholds. And this leads to results that are not smooth, which some people feel is a drawback in regression, but I really don't think so. The CART algorithm has 3 parts: a way to select a split at a terminal node, a rule for declaring a node to be terminal, and a rule for estimating y at a terminal node. And the third part is easy. You just find the sample average for the cases at the terminal nodes. So you wind up in a terminal node and you average all the response values at that node. And the first part is also easy. You split on the value x star sub j, which most reduces the sum of square error in the fit. So you'll make the split such that the new sum of squares error is as small as possible. And that's what you would like to do. I will note that Andreas Buya did some work that hasn't gotten as much attention as I think it deserves, but what he was able to show is that very often, if instead of trying to make the split that reduces the total sum of squares error, you might make the split that reduces the sum of squares error the most on one side and doesn't much reduce the sum of squares error on the other side. So you might find there may be a better split in terms of the total sum of squares error, but if you can get as much purity on one side of the split as you can, that often leads to better prediction. The second part is the hard one. The second part, of course, is to find a rule for declaring a node to be terminal. And typically what CART does is it draws an overly complicated tree, and then it uses a pruning rule or cross-validation to find a tree with good predictive accuracy. So they're going to be using a complexity penalty to reduce the overly complicated tree. And the main problems with CART are, some people don't like its discontinuous boundaries. It's difficult to approximate functions that are linear or additive in a small number of variables. So if you actually did have a linear relationship between an explanatory variable and the response, the best CART can do is to sort of have a stair-step function. So it'll take a step along x1. So if it's a linear relationship between x1 and y, it'll take a jump from x1 equals 0 to x1 equals 1. It'll fit another region between x1 equals 1 and x1 equals 2, and so forth. CART is usually not competitive in low dimensions, but it does remarkably well in higher dimensions. And you cannot tell when a complex CART model is close to a simple model. That tends not to be easy. And the Boston housing data give you an example of that. Here is the famous Boston housing data. They were trying to predict the price of a home in Boston from information on number of rooms, crime rate, LStat, which I think is something about social status, the amount of industry in the area, a whole batch of explanatory variables. And their CART tree did a good job of estimating the prices of these homes, but Andreas Buya came along and said, you know, let's just reduce the variance on one side of the split as opposed to reaching the sum of the variances after the splits. And when he did that, he got a beautiful CART tree that split on crime rate, crime rate, crime rate, crime rate, crime rate, crime rate. And then the last question is, do you have a view of the Charles River? And that's much more interpretable because it was saying that the price of a home is basically driven by the amount of crime in the neighborhood, or it's associated with the amount of crime in the neighborhood. And there's a little bit of niceness from having a good view. So that's what's going on with classification and regression trees. Jerry Friedman wanted to combine CART with projection pursuit regression. And so he developed multivariate adaptive regression splines, and it uses multivariate splines to let the data find flexible partitions of RP. So instead of splitting in alignment with the natural axes, the way you have in this diagram, he wanted to let projection pursuit regression determine splits that were not aligned with the natural axes. And the approach is based on tensor splines, and the basic building block is a hockey stick function that looks like this. It's 0 below t, and it takes a 45-degree angle for values above t. And for people who do deep learning, this looks a lot like ReLU. The fitted model has the form y is equal to a sum over r terms of a weight beta j times capital B sub j of x. And the B sub j are products of these hockey stick functions. And Jerry insisted that whenever a hockey stick function is added, the negative of that hockey stick function is also added. And the reason he did that was he wanted to ensure that these were this model was equivariant. So if you multiplied x1 by -1, you'd still wind up fitting the same approximation. So the beta j terms are the product of hockey sticks, and that means that the fitted functions are going to be continuous, and the regions are determined by the knots in the t sub jk. And the Mars algorithm starts with beta 1 identically equal to 1, and then it adds new terms into the product until there are too many as measured by generalized cross-validation. And you'll recall that generalized cross-validation was that approximation based on the hat matrix, the average of the trace of the hat matrix. Empirically, Jerry found that each term in a Mars model costs between 2 and 4 degrees of freedom, and that reflects the variable selection involved in the fitting more than the smoothing. Here's the algorithm. For each basis function B sub j, you look at all variables not in B sub j, and you try putting plus or minus hockey sticks at every observation, a candidate not, in the non-zero region of beta j. And this certainly reminds me a lot of the CART, where you consider all possible splits. And then you select the pair of hockey sticks that, according to an estimate of lack of fit, and that would probably be assessed through cross-validation. Then we add the two new basis functions into the product B sub j, and we go forward. And you do that for each of the basis functions. And after you build too many basis functions, you prune back by using cross-validation to eliminate basis functions that are not needed. So surprisingly, Mars is a little bit interpretable because we can have sort of an ANOVA decomposition. The fitted function f hat that we get can be written as a sum of functions that depend only upon one of the explanatory variables, plus a sum of functions that only depend upon two of the explanatory variables, and so forth. And so you can think of this as main effects, two-way interactions, and so forth. And if the logical experimental design is actually helpful here, then we can imagine that we probably wouldn't have very many terms that are three-way dependencies. So Mars uses a tensor product basis. Additive effects are captured by splitting beta 1 on several variables. Nonlinear effects are captured by splitting beta 1 with the same variable more than once. And so, like Mars does automatic variable selection, it may not choose to use some of the explanatory variables in any of its tensor products. Okay. We're about to start with variable selection, but I think this is probably a good time to pause and ask if anybody has any questions.
Thanks, David. We have here a couple of questions. The first question is from Vinod Kumar. Is asking if can we apply a non-parametric regression model for predicting the climate variables for germplasm collection sites?
I assume that you can. I know that non-parametric regression is used by a lot of statisticians who do spatial statistics to study climate, but I've not done that myself, and I think I would refer you to papers by people like Richard Smith.
Thanks, David. The other question is from Dr. Mutija. The question is, the data satisfying the conditions of parametric the data satisfy the condition of parametric regression, but be analyzed by non-parametric regression. Can it be done? So essentially asking, the question is whether data that satisfies the condition for parametric regression can be analyzed by non-parametric regression.
Yes, you certainly can, but if you actually do know what the parametric family is, say that it's multiple linear regression, say, if your data are generated by a multiple linear regression model, then it would be better to just go ahead and fit the multiple linear regression. However, if you do not know that the data come from a multiple linear regression, then you could certainly use non-parametric regression techniques, and the generalized, the additive model would be a very natural thing, and what you would find would be you get smooths that were very, very close to flat surfaces.
Yes, perfect. Thanks, David.
Okay.
So should we make a break? How long would you think of?
I would like to take a break. I'd like to have a 5-minute break if we can.
Okay, perfect.
Thank you so much.
Thank you. David, welcome again, and welcome everyone again. We have here one next question. It is a general question. Is from Vinod Kumar. Is asking, which is the most commonly used regression model?
Most commonly used non-parametric regression model.
Maybe you can answer in that direction. I think he's asking in general. In general, I guess that linear regression is most used, but maybe you can talk about also nonlinear regression.
Certainly, the linear model, linear regression, is widely used, and that's certainly what economists and so forth go to as their first choice. Among the non-parametric regression methods that I talked about, the two that stand out for me are CART and the simple additive model. And I think there's a lot to be said for both of those. There are a handful of circumstances in which you would have domain knowledge that makes you think that a projection pursuit regression model might be superior to the additive model. But in general, I think it's largely between CART and the additive model. MARS has fallen out of favor. People have moved on to other things. So I think that's my answer to you.
Thank you very much, David. There are no more questions at the moment, so we can continue. We'll put on your slides.
So our next unit is on variable selection, which of course pops up whenever we have a lot of explanatory variables, some of whom may not be relevant to the response that we care about. And this is particularly challenging when the number of explanatory variables is larger than the number of observations that you have. And in the mid-2000s, a lot of work was done on variable selection. And we're going to talk about ridge regression, the LASSO and some of its relatives, the Dantzig selector and some of its theory, Peter Hoff's method, and something called the median model. So variable selection and the related topic of dimension reduction are very active areas of research in the data and analytics community. And this review is only going to be able to talk about a fraction of all the work that is being done on that topic. So ridge regression is an old idea, and it was originally used to protect against multicollinearity. It shrinks the coefficients in a regression towards zero, and incidentally towards each other, by imposing a penalty on the sum of the squares of the coefficients. And so we're going to seek beta hat, which is the argmin of this thing. It minimizes the sum of the squared discrepancies between the observed value and the predicted value, but it also is trying to keep the sum of the squares of the coefficients from growing too large. So that is what we're trying to do. And I'll note that beta naught is generally not part of this minimization. So this beta is simply the beta 1 to beta p coefficients in that vector. And you may recall Stein's result that when estimating a multivariate normal mean with squared error loss, the sample average is inadmissible, and it can be improved by shrinking the estimator towards zero. And that's sort of the intuition behind why this might be a good thing to do. Neural networks also do a similar shrinkage on the weights at each node. We call that quantization when I discussed it earlier today. Ridge methods are not equivariant under scaling, so one normally standardizes the x sub ij with respect to j, so that each of the explanatory variables has unit variance. And traditional ridge regression solves beta hat is equal to x transpose x plus lambda times I inverse times x transpose y. And the fact that we have added lambda to the diagonal of the x transpose x matrix is what gives us a ridge on that diagonal, and that's where the name comes from. You'll note that this increases the trace of the hat matrix, which corresponds to increasing the degrees of freedom that are used in fitting the model. Ridge regression and shrinkage methods in general can be seen as the Bayesian posterior mode for a suitable prior. And there's a one-to-one correspondence between a penalty in the non-Bayesian world and a prior in the Bayesian world. And for ridge regression, this penalty corresponds to a prior that assumes that each of the coefficients beta j has an independent normal distribution with a common variance. Rob Tibshirani was thinking about this, and he decided that maybe it would be nice to have a variation on the ridge regression. Instead of finding the value of beta that minimized the sum of the squared discrepancies subject to a penalty on the squares of the coefficients, he put a penalty on the absolute values of the coefficients. So we don't want the sum of the absolute values to be too large. And often in practice, what you see are trajectories of LASSO solutions corresponding to minimizing the sum of square deviations subject to this constraint that this thing be less than or equal to S. So we can vary lambda, and that will correspond to giving us a set of trajectories for the solutions. If S is larger than the sum of the absolute values of the least squares estimators, then the LASSO is going to agree with ordinary least squares. But if S is small, then many of the beta j terms are driven to zero, so it's performing automatic variable selection. Yes, okay. The Bayesian prior corresponding to Rob's penalty is the Laplacian prior, and you'll note that the Laplacian prior tends to put a lot of weight near zero and less weight far away. So it's favoring solutions in which the estimated coefficient is zeroed out, and it's putting much less weight on cases in which the coefficients are very different from zero. And there's a famous illustration of what's going on here. Unlike ridge regression, the LASSO is apt to drive the coefficients to zero. And that's especially true when the penalty is pretty tight. To see what's going on, the left graph shows how the contours of the ordinary least squares estimates intersect with the constrained space for the LASSO versus the right graph, which shows the same situation with the constrained space for ridge regression. And for ridge regression, the constrained space is a circle here. Here it's a diamond. And you'll see that this ordinary least squares fit. Those estimates are more likely to hit at a corner point for the LASSO than they are for the ridge regression. And so that is why the LASSO tends to give you answers in which some of the coefficients are equal to zero. Here's an example of the trajectories that you get from ridge regression as you relax the penalty. So we relax the penalty, and what we see is that we, well, first of all, you note that all the coefficients start being non-zero very early on, and then they change, and you'll note that sometimes you even have coefficients that start off positive, but then become negative as the penalty is relaxed. So compare that with what we get with the LASSO as we relax the penalty in the LASSO. In the LASSO, we don't have everything becoming non-zero at once. Rather, one variable becomes non-zero, and then later on, a second variable becomes non-zero, and then later on, a third variable becomes non-zero. Furthermore, you'll note that the signs of the variables never change. If it's positive when it starts off, it's going to stay positive. If it's negative when it starts off, it stays negative. And so those seem like very nice properties for the LASSO to have compared to ridge regression. The LASSO's penalty region looks like this. Ridge regression has a penalty region that's a circle, and these correspond to LQ penalties. And ideally, we'd like to use an L0 penalty, which simply minimizes the number of non-zero coefficients. If we do that, then we have direct variable selection. But that's going to entail non-convex optimization. This is convex, this is convex, this is convex, but once we get a Q below 1, it's no longer convex, and that means that traditional techniques are going to not work well, and the solution is not going to be unique. But typically one finds that non-convex optimization, that even though the solutions are not unique, very often the solutions are similar in terms of their mean squared error or their predictive behavior. The L0 penalty strongly favors sparse solutions, but the penalty is not convex, so the solution is difficult and often impossible. So consider L2 minimization with an L0 penalty. So we want to minimize the sum of the squared discrepancies between the observed value, the observed response, and the predicted response, subject to lambda times the number of non-zero coefficients. And the non-convexity of the penalty means that one has to perform combinatorial search in order to find the solution. But in some situations, solution is still possible, and in that case, we call this the Danzig selector. And it was developed by Emmanuel Candes and Terence Tao. The Danzig estimator, beta hat sub d, is based on the fact that often the L1 solution agrees with the L0 solution. And so beta hat d minimizes the L1 norm of beta, subject to the condition that this dot product is less than a constant times the variance times the square root of 2 times the logarithm of the number of explanatory variables. And you'll note here that the intercept is not part of this beta that we're trying to solve for. And it turns out that if the number of non-zero elements in the true beta is k less than n, then with high probability, the Danzig estimator does asymptotically as well as it could have done if the identities of the non-zero components were known in advance. That's an oracle property. So if the number of active explanatory variables is truly less than your sample size, then this has a good chance of working for you. A second framing of this same problem is due to David Donahoe and I think it's Martin Tanner. They consider the noise-free case in which y is equal to x beta, but x is n by p with p greater than n. So it's an ill-posed problem, and in principle, you're not supposed to be able to solve this. But in the following diagram, if the vertical axis is k over n, where k is the number of actually useful explanatory variables, and the horizontal axis is n over p, then there's a phase change that occurs somewhere between the boundaries. And above the upper line, solution is impossible. Below the lower line, with high probability, the solution can be found. And I'll say some more about that in a minute. So up here, you have no chance. The red region, you can't solve it. Down here, yes, you probably can solve it using the Danzig selector or some other tool. And in here, in the purple region, we just do not know whether or not a good solution can be found or not. And it turns out that whether or not a good solution can be found is related to the property of a projection of high dimensional polytopes onto lower dimensional spaces. So here we have a three-dimensional cube that's being projected onto a two-dimensional surface. And you'll see that if the vertices on the polytope in the three-dimensional space are exterior vertices in the low-dimensional space, then in general, you can solve the problem and get the answer. But if the projection is to an interior vertex, such as this one or this one, then solution is essentially impossible. So that's the situation, and all of this is based. I really admire David Donahoe's ability to find math literature that you wouldn't think would be relevant and then do amazing things with it. There's an old mathematician at McGill University who was looking at whether or not projections of high-dimensional polytopes to lower-dimensional surfaces would have exterior vertices or interior vertices. And this was all back in the 1960s. Nobody really thought that this work would go anywhere. It was an interesting sort of geometric curiosity. But David was able to make this the foundation for the phase change phenomenon that he observed here. There's a third approach to P greater than N regression, and that's due to Martin Wainwright. And he showed that under certain assumptions on X, then with high probability, the LASSO correctly identifies the non-zero elements of beta. And in particular, if N is greater than 2 times K times log of P minus K, where K is the number of relevant variables, then the probability the LASSO succeeds tends to 1. And if N is less than 1/2 of K times the natural log of P minus K, then the probability the LASSO succeeds tends to 0. And so these correspond to the blue and red regions of the phase change diagram. All three of these approaches, by Candes and Tao, Donahoe and Tanner and Wainwright, they all show that under various conditions, sparse linear regression can work even when the number of potential explanatory variables is much greater than the number of observations. So that's all great. But wouldn't it be nice to have a way to directly solve the non-convex optimization and impose an LQ penalty on the sum of squares minimization, where Q is less than 1, but of course greater than 0? I will note that these results for linear regression probably also hold for non-parametric regression. Larry Wasserman, John Lafferty, and some students attempted to extend these methods to non-parametric regression based on additive models and generalized additive models. They call their method SPAM, for sparse additive modeling, and a combination of simulation and theory suggests that it works fairly well. After that paper came out, there was another paper that said it was rejected from STAT that showed that projection pursuit regression had the same phase change phenomenon that Donahoe and Tanner found. Simulation studies suggest that this phase change phenomenon is pretty general, but there's really not much theory that is out there yet. Regarding the P greater than N classification problems, less statistical work has been done, but people believe that the problem is similar to regression and maybe even a little easier. So, I said it would be nice if we could have a way to directly minimize with an LQ penalty for Q less than 1, but greater than or equal to 0. So, the LASSO is finding beta hat to minimize this thing, and that's equivalent to minimizing beta transpose Q times beta minus 2 beta transpose L plus the lambda times the norm of beta 1. And we're going to write X transpose X is equal to Q, and L is equal to X transpose Y. And that, depending on how facile you are with linear algebra, that may or may not be obvious, but if you just write it all out, that's what you get. And now Peter Hoff suggested we reparameterize the model so that beta is equal to U Hadamard producted with V. So the Hadamard product is the element-wise product. So U1 times V1, U2 times V2, and so forth for these vectors U and V. Then we can rewrite this minimization as G of this minimization here as G of UV is equal to U composed with V transpose times Q times U composed with V minus 2U composed with V transpose L plus lambda times U transpose U plus V transpose V over 2. And Peter was able to prove that the infimum over the F minimization is equivalent to the infimum over U and V for the G minimization. And if U hat and V hat is a local minimum of G, then beta hat equals U hat composed with V hat is a local minimum of F. So if you can solve the G problem, that's the same as solving the F problem. Now, G is differentiable and biconvex, so its local minimizers can be found by using an alternating ridge regression algorithm. And to see this, we can write out this as U transpose Q composed with V transpose U, and U composed with V transpose L as U transpose V composed with L, so forth. That's just rearranging the parentheses. And so we can rewrite this G transformation of this G function that we want to minimize. And this is quadratic in U when V is fixed. And though it's going to have a unique minimizer at this thing. And symmetrically, the unique minimizer of G when U is fixed is going to be this thing. And so what you do is you alternate back and forth. You pick U and V to start, and then you alternate back and forth, doing first the minimization with fixed V, then the minimization with fixed U, and you're going to converge to a solution. And that's going to give you a stationary point that is a local minimum because, well, that's just the way it all works out. And and then Peter said, let's generalize the Hadamard product representation. So instead of having U1 composed with U2, we have U1 Hadamard product with U2 ... Hadamard product with U sub K. And then you can roll through minimizing with respect to U1, holding the rest constant, then minimizing with respect to U2, holding the rest constant, and you just cycle on that, and you can solve to find U hat 1, U hat 2, U hat K that minimize, that are a local minimum. When K is equal to 1, then we're just doing the L2 penalized ridge regression estimator. When K is equal to 2, we get the L1 penalized LASSO estimate. And when we have values of K that are greater than 2, then we're grading LQ penalties for Q equals 2 over K. And this is, I think, breathtaking. This is a very fast algorithm. It's totally trivial to program. And you can take K pretty damn large and not have any problems at all. So you could take K equals to 100, and then you'd be using a Q penalty of 1/50th, and that's going to be very, very close to what you would like to get in this picture back here. So that's going to be really, really close to the L0 penalty that we want. So if I were doing a problem and I wanted to try and do automatic variable selection, I would look to Peter Hoff's method before I would look to the LASSO. I think it's got enormous potential. Peter has experimented with the non-uniqueness. So if you start it from different initializations for U1, U2, etc., you wind up typically in different minima. But these minima, he says, are all close together, and so they're all performing about the same. Now I'd like to talk about Bayesian methods for variable selection. And the standard Bayesian strategy for variable selection is to use a spike and slab prior on the coefficients. So here's a spike and slab prior. We're putting a lot of weight on 0. With probability 1/2, we think that the coefficient is 0. And with probability 1/2, we think that the coefficient has a normal distribution. So that's our prior, and we update that with the data. And this strategy is very similar to the Laplace double exponential prior that is the Bayesian interpretation of the LASSO. But there are other interesting Bayesian approaches, and the median model approach of Barbieri and Jim Berger is one that I think has some interesting properties. Assume that there are p explanatory variables, and one wants to consider a model of the form y is equal to the explanatory variables x times a vector beta I star that depends on some, maybe all, of the p explanatory variables. So we're going to let I run from 1 up to 2 to the p. So the first variable can be in or out. The second variable can be in or out. They're p variables, so there are a total of 2 to the p possible models if we exclude the degenerate model in which none of the variables are used. So we're going to assume that this is all happening without worrying about the intercept. So beta transpose I is equal to beta naught plus this beta I transpose. That should be transpose 2. And thus xi is going to be a submatrix of xi star, the full matrix. And that's what we're going to look at. We're going to let the length of beta I be d of I, and we're going to let the density corresponding to the model m sub I be f sub I of y, given whatever coefficients we're using and sigma squared. And in this case, there are two standard choices for the parameters, for the priors on the parameters in m sub I. These include the G priors and the Zellner-Sau priors. And I don't think it's very helpful to really dwell on these different priors. The important thing is that they're two standard choices and they're easy to compute. With these definitions, the marginal probability of the data y under the ith model, we're going to denote that by lowercase m sub I of y, and that is going to be the integral of the density for the y's multiplied by one of these priors that we get here, either the pi g or the pi zs, and we go from there. And if all models have equal prior probability, then the posterior probability of a particular model is simply going to be the probability of m sub I given y is the marginal for the ith model of y over the sum of the marginals for all of the models. So that's pretty standard Bayes. And in this case, the posterior inclusion probability for the ith variable, that should be the jth variable, sorry. The posterior inclusion probability for the jth variable is q sub j equals the probability that beta j is used in the correct model given y, and that's going to be the probability of the posterior probabilities of each of the models times an indicator function for whether beta j is in the kth model. And if all of that is lead in, well, it turns out that the median probability model is the model that consists of all and only those variables whose posterior inclusion probability is at least 1/2. Paolo, let me ask, does anybody have any questions so far?
There is a couple of questions. Do you want me to read them to you?
Are they about the median model that I'm talking about now, or are they about older stuff?
They are about VMod is asking about how to select subset of significant predictors from all the potential predictors.
Okay.
I think
that is certainly relevant to what's going on here. And maybe the right answer is simply to finish the median model and see if that answers the question. It probably won't, but it's a starting point. It turns out that the median model is generally superior to the maximum posterior probability model in terms of prediction. And there's a theorem from Barbieri and Berger that consisted of a sequence of nested linear models. And if you want to make predictions for covariates that are similar to those you've seen already, and if the posterior mean under m sub I satisfies this mild condition, then the best single model for prediction under squared error loss is going to be the median probability model. And that second condition is satisfied if one uses either of the non-informative priors, if one uses either non-informative priors for the model, or if you uses the G-type priors with the same constant C for each model. So this theorem actually is not very restrictive.
Yes, and this was the only question that we have now.
Okay, then I'm going to go forward, and then we'll pause and see if there are follow-up questions. So in order to test this or to illustrate this, Jim did polynomial regression, and he had data from this where the correct model is M3. So we have a cubic term, but not a quartic term in this. He generated data from that, and then he found the Bayesian posterior probability of the model with no terms, and that posterior probability is essentially 0. The posterior probability for a model with exactly the linear term in it was 0.06. The posterior probability for the model with linear and square terms is 0.22. For cubic terms, it's 0.29. But the maximum posterior probability is achieved for the quartic model, which involves x to the fourth, and that has posterior probability 0.38. When he does the median model, we see that the probability of including 0 is probability of including a constant is essentially 1. The probability of including a linear term is approximately 1. The probability of including a quadratic or cubic terms are both bigger than 0.5, but the posterior probability of including the fourth term, the quartic term, is below 1/2. So this correctly finds the M3 model, whereas the maximum a posterior model is M4, and that's wrong. But for variable selection, the model space is so large that one needs to use guided search. So you want to find some reasonably good model and then search more intensively in their neighborhoods. So at any stage, let M sub 1 up to M sub r denote models that we have previously studied. And I'm going to define the current estimated posterior probabilities of a model, assuming equal prior probabilities for everything, as the marginal from the data for the ith model divided by the sum of the marginals for all of the data for all of the models we have seen so far. And that's not going to be the true posterior probability because we haven't looked at all the models, but it would approximate the posterior probability. Now we define the estimated variable inclusion probabilities as Q sub j equals the approximate posterior probability that beta j is in the correct model given the data. And that's going to be the sum from I equals 1 to r of the approximate posterior probability of the ELF model times an indicator function for whether beta j is in the ELF model. Now, at the next step, at iteration r plus 1, we compute the current posterior model and inclusion probability estimates p hat m sub I given yi, and we find qj. We return randomly to one of the previous models that we've already visited with probability proportional to their estimated posterior probability. So if it's a really good model, we're very likely to return to it. If it's not a great model, we're less likely to return to it. And then we add or remove a variable with probability 1/2. If we add a variable, we choose the jth variable with probability proportional to qj plus c over 1 minus qj plus c. And so, and qj, you recall, is the inclusion probability. So if it's likely to be included, if it's got a high chance of being included, we're more likely to add it. If we are removing a variable, then we choose the jth variable to remove with probably 1 minus qj plus c over qj plus c. And here c just keeps qj bounded away from 0 or 1, and using 0.01 seems to work well. If in step 3 we obtain a model that we've already seen, then we go back to step 2 and choose a different model and go through. But if it's a new model that we haven't studied before, we update the estimated posterior probabilities of the ith models, and we update the estimated inclusion probabilities for the jth variables. And then we return to step 2. And we keep going until we get tired. as an example of how this works, recall the pollution data that Leo Breiman and Jerry Friedman used in their ACE paper. Barbieri and Berger refit that data. And the ozone data has 178 observations and 10 covariates. And Barbieri and Berger considered linear models with an intercept and all possible main effects, quadratic terms, and two-way product interactions. So they had a total of 65 covariates, and 2 to the 65 is big. So they used the G priors and the Zellner-Sau priors for computational reasons largely, and they implemented the algorithm at different starting points, which is called random restart, and they found essentially no difference in their results. They made 5 million iterations and saved only the best 65,536 models. And none of those best models had very much posterior probability. The largest model, the model that had the largest posterior probability, that probability is only 0.0025. The following partial table shows the estimated posterior probabilities for variable inclusion in the ozone problem discussed in the ACE section. So X1 should be included. X2, according to the median model, it should not. It's below 0.5. X3, don't include it. X4, definitely include it. X5, exclude it. X6, exclude it. X7, exclude it. X8 should be included. The quadratic term X1 times X1 should be included, and so forth. And what was very clever about this is that Jim Berger noticed in the ACE paper that the transformations of the explanatory variables tended to be pretty linear or pretty quadratic. And so that meant that he could look at the class of models that had linear, quadratic, and interaction terms as a rich class that would have a lot of models in it. But he also was fairly confident there would be some very good models among those, because ACE found that linear and quadratic terms worked very nicely. So that's what's going on. And you can see that there's a little bit of a difference between using the G prior and the Zellner-Sau prior. So, for example, the X1 times X2 thing, 0.57 is considerably less than 0.73. So there's variation. Now I'm going to speak to what I think is the question that was being asked about strategies for finding subsets of good variables. And we don't have to use the Bayesian approach to implement the search strategy, the guided search strategy that Barbieri and Berger used. So we could choose model features, which might be variables, graphical nodes, structure, and we want to use these to drive the search. We're going to choose a criterion for defining a good model. And as an example of that, it might be Akaike's information criterion, but it could just be something else. Now we convert that criterion into pseudo probabilities for each of the models. So we might say that the pseudo probability for the ith model given y is e to the AIC for the ith model. Then we define the feature inclusion probabilities in sort of the obvious way. It's the estimated pseudo probability times an indicative function for whether or not the jth feature is in the ith model. And then you apply the search algorithm exactly as before. And now I'd like to make a few comments about high-dimensional search strategies. Effective search in large, non-orthogonal situations requires guidance, revisiting high-probability models and changing variables in their neighborhood according to posterior inclusion probabilities seems to be an effective way to explore some very big model spaces. There's no model with significant posterior probability, but there may be many thousands with roughly comparable posterior probability. And in these situations, my sense is that you probably don't want to pick a model. You want to pick an ensemble of models and use that. And generally, the ensemble will provably be better than any of the models in any single model that you could select. In the case, however, that it's more important to deliver insight and interpretation, then the posterior inclusion probabilities for each of the variables is very helpful. That tells you which variables are explanatory and which ones are apparently irrelevant. Often one compares predictive accuracy between two models with different variables, and racing is a strategy invented by computer scientists to extend the reach of the model space search that you can do. And what they point out is that if we fit a random 1% of the data to model 1 and the same random 1% of data to model 2, that may be sufficient to make it really clear that model 1 is better than model 2. So then we discard model 2, we go to model 3, and we fit a random 1% to model 3. And if it's not clear that which of model 1 and model 3 is better, we can add another 1%. And usually by the time you get to 5% of the data, it's very clear which model is better. So we don't have to fit all the data to every model in order to do model selection. And so it's an easy way to extend one's search capability, and empirically, it extends it by a factor of about 100. So if you're in a situation where you're doing a lot of model search, that's valuable. And now I'm going to pause again and see if there are any questions.
David, so far so good. No questions at this moment.
Okay. I would like to specifically ask if what I've said was responsive to the question about how you do subset selection.
I will, maybe we can because this was asked by Vinod. We can, if I will ask Vinod to write back on YouTube, sure. And when he does, I will let you know.
Thank you so much.
If the answer will be negative, of course.
Okay, that's cool.
Yes.
Well, we have gone through the units on classification on regression that I'd originally planned to talk about. And if you all are up for it, I would like to say a little bit about classification, because in many ways, that's a very similar problem. So, hearing no objections, classification problems attempt to find rules that assign cases to categories. And so it might be deciding whether or not an income tax return is correct or incorrect. You might want to do medical diagnoses. Does a person have a flu? Does he have COVID-19? Does he have smallpox? Does he have the measles? Those would be a classification problem. Banks try and decide if people are good credit risks or bad credit risks. And you could imagine that pollsters might decide whether a person is a Republican or a Democrat or an independent. And as with regression, one has a training sample of cases for which the categories are known, and each case has a vector of covariates that are used to build the classification rule. And when there's a new observation, one looks at its covariate and classifies it according to the classification rule. And there's generally sort of three types of classification rules. One is geometric, which includes discriminant analysis, flexible discriminant analysis, and recursive partitioning. A second category are the algorithmic rules, which include neural nets, nearest neighbor rules, support vector machines, and random forests. And then there's the class of probabilistic classifiers, which includes Bayes rules and hidden Markov models. And the probabilistic methods tend to make strong assumptions about having random samples of data. The other two categories don't typically need that much. Most classification problems are very similar to regression problems. For problems with two categories, it's sometimes as simple as fitting a model that predicts either 1 or -1 according to the case label. Discriminant analysis is an easy one to talk about. It's one of the first of the geometric rules, and it started with Fisher's classification of the iris species Versicolor virginicus and setosa. And here we have trellis plots of the sepal length, sepal width, petal length, and petal width for samples of irises. And you can see that the red and the blue and green often separate. The red is easier to classify than the blue and green, which seem to be more intermixed. Nonetheless, it makes sense to try and use these 4 measurements on sepal length, sepal width, petal length, and petal width to try and develop a classification rule. And linear discriminant analysis assumes that one has a multivariate normal measurements on random members from each of the populations, and that one knows which individuals are from which population in the training sample, where the populations have different means but a common covariance matrix. And then one finds hyperflats, which assign previously unseen members to the most likely population. So here, for example, this is the first discriminant surface, and it appears to be separating the yellows from the blues and the greens. And here's the second discriminant surface, and it appears to be separating the blues from the yellows and greens. So we only need 2 such separating surfaces in order to classify 3 things, 3 types. So if it's on this side, we say it is type blue. If it's on this side, we say it is type green, and anything left is type yellow. For 2 classes, linear discriminant analysis assigns a new observation to the group whose mean has the smallest Mahalanobis distance to the observation. So if we have x bar 1 and x bar 2, a new observation xi is going to be assigned to either group 1 or group 2 according to whether it minimizes the Mahalanobis distance written here. And to analyze the effect of noise in linear discriminant analysis, suppose one has a fixed sample size n and assume the covariance matrices are known to be sigma squared times I. So that means that I can write the means at these noisy means as being equal to the true mean plus something that goes to 0 at rate square root of n. And similarly for this, it's going to be the true mean plus noise terms that go to 0 at the rate root n. And I'm going to write a new observation that we want to classify as x is equal to mu1 plus noise. Fisher's classification rule is going to assign it to population 1 if the Mahalanobis distance to mu hat 1 is less than the Mahalanobis distance to mu hat 2. And if you sort of rewrite this, that's going to be equivalent to having x minus mu hat 1 transpose times x minus mu hat 1 being less than x minus mu hat 2 transpose times x minus mu hat transpose, x minus mu hat. And we're going to rewrite x mu hat 1 and mu hat 2 in terms of the v, v1, v2 that we had over here. And in that case, this criterion becomes this thing. And there's a little bit of algebra to simplify things around, but that's what it comes down to. And if we rewrite it again, we can see that this is going to be equal to mu1 minus mu2 minus sigma over root n times v1 plus v2 plus 2 sigma v transpose times the thing without the transpose. And as n goes to infinity, this criterion is going to converge to whether or not 2 sigma times v transpose times mu1 minus mu2 is greater than the norm of mu1 minus mu2, or the squared distance between mu1 and mu2. And that means that the probability asymptotically of misclassification is going to be the probability that our noise is greater than the distance between the means divided by the standard deviation of the noise. And that's a signal to noise ratio. The strength of the signal is how far apart mu1 and mu2 are with respect to the noise, which is 2 sigma or sigma. So asymptotically, this is not a surprise. The signal to noise ratio should determine whether or not we're in a situation where our points are widely separated or all mixed up. But if we don't rush forward to do the asymptotics and instead consider the curse of dimensionality situation, then the rule assigning population 1 can be written this way. It's going to be whether this thing is larger than this. And so the probability of misclassification is going to be 1 minus the cumulative distribution function for the standard normal of negative 1 over 2 sigma times the norm of mu1 minus mu2 times 1 plus 2 sigma squared over the norm squared p over n to the 1/2. So let's look at what happens when p gets large, but n is small. So as p gets large, this thing goes to infinity. And if I multiply infinity by -1, then I'm going to get negative infinity. So the standard normal distribution evaluated at negative infinity is 0. So the probability of misclassification is going to go to 1. And that means that the curse of dimensionality is going to hammer the discriminant analysis approach in a serious way. And this isn't a surprise, really, because we know that the curse of dimensionality applies very generally, not just to regression. And if one digs into the literature, you'll find that the curse of dimensionality hits classification as well, no whether doing linear discriminant analysis or not. One issue with linear discriminant analysis is the danger of overfit. And here we have the red test data and the green true data. And I apologize to people who are colorblind. I took these slides from the first edition of the Elements of Statistical Learning, because if you teach using that book, you're allowed to use their images. But they used red and green, and I wrote to Rob and suggested that he change the color palette, and the second edition did. So it's now sort of cyan and brown. In any case, what we see here is that the test data would go, if we overtrained it and used the training data, we would sort of get our best performance when we had 6 dimensions. But in the test data, we see that the best performance occurs when there are 2 dimensions used in the training set. I'd like to talk about nearest neighbor classification, and that's one of the algorithmic methods that we talked about. And a very reasonable approach to classification is k nearest neighbors. In order to make a prediction about a new observation, one looks at the labels of its k nearest neighbors and uses a majority vote to make the prediction. And if there are more than 2 labels, then we would use a plurality rule. So if we're trying to classify people as trying to classify a medical disease as being COVID-19 or smallpox or the flu, then we take not the majority rule, but the plurality rule. If 40% of the neighbors were flu, then we go with flu. As the number of neighbors used in making the prediction increases, the decision boundaries become smoother. The bias increases, but the variance decreases. So it gets smoother. And the degrees of freedom for a nearest neighbor rule is going to be n divided by k. So if we have a total of n observations and we use k nearest neighbors, then the degrees of freedom that's involved is going to be n over k. The following images show how the nearest neighbor classification rules perform on data simulated from a 20-component mixture model, half of which were red and half of which were green. And the effect of the bias variance trade-off is very clear. So here is just doing linear regression with +1 and -1 to fit the labels. Here we're doing nearest neighbor classifier with 15 nearest neighbors. And so that's a fairly smooth decision boundary that we get. Here we are doing nearest neighbors with in which we're looking at the one nearest neighbor. And so you see that this has a lot of variation in the boundary. Not much bias, but a lot of variation in the way the boundary looks. If we look at the misclassification in the nearest neighbors, what we see is that the training set does best when the number of nearest neighbors used is around, well, when n over k is around 8, whereas the training set, gets better and better as you move to higher degrees of freedom. So as k equals 1, you get really poor performance. So the purple line here in the middle shows the performance of the Bayes classifier, and that's the optimal classifier. And they were able to calculate this because they knew the 20-component normal from which the data were generated. Here is the Bayes rule boundary that separates the red points and the green points. And so we've written that in here, and that's the best you could do for the classifier rule. Here, Hasty, Tibshirani, and Friedman used a neural network to estimate the classifying rules, and they used no weight decay. Weight decay is when you shrink the node's weights towards zero. And if you look very closely, you can see that we still can have the purple line that represents the Bayes rule. And you can see that the neural network with no weight decay is not coming very close to the Bayes rule. However, if we do use weight decay, then you see that the neural net classifier is not bad. It comes pretty close to the optimal classifying rule, and where it breaks down, and basically in regions where there's just no data. So it's very hard for a neural net classifier to learn a good rule out here when there's no information. And it's been about an hour since we last took a break. So I suggest that maybe this is a good point to pause, and we come back, say, in 5 minutes. That works.
That's great. David, do you mind if I ask you a couple of questions from Vinod?
Please, yes, go.
So the first of them is, can we use the discriminant analysis method to classify the large number of geoplasm lines occurring to their maturity group or flowering duration? It is a specific question, I guess, from this area of research.
I think the answer is that yes, you could, although I would not reach to discriminant analysis as my first tool for that classification problem. They're much better tools than something that was invented back in, I think, 1933.
Yes, thank you. And the next one is, please explain the difference between Fisher classification and Fisher tests.
There are a lot of Fisher tests out there, so I'm not quite sure which one you would want to use. Fisher's classification rule is discriminant analysis, and it's a very simple rule. It makes very strong assumptions. It's been generalized so that instead of having linear separators, you have quadratic surfaces that separate, and that's called quadratic discriminant analysis. But Fisher's tests, I imagine that's probably referring to the F test that's used in the analysis of variance, which is a problem that is very different from what we're talking about now.
Okay, right. I think those are the questions that we have for now.
Okay. Then let's return at in 5 minutes at 4:12.
Okay, perfect.
Thank you.
Perfect. David, welcome back again. Welcome back, everyone. Meanwhile, Vinod clarified he was talking about the Fisher exact test.
Fisher exact tests. Okay. That's a very different type of thing. And it's used in contingency tables. And that's, I think, different from what we're talking about today.
Mm-hmm. Yes.
Okay.
So, David, there is no more comment for now. I think we can continue, and we can finish as soon as you wish. We have maximum 45 minutes.
Right.
So just feel free to manage the time.
Okay. Thank you so much, Paolo.
Thank you.
I'd like to talk about support vector machines, which are a very exciting area. They were invented by Vladimir Vapnik, and they use optimization methods to do the classification. Their key innovation is to express the surfaces in terms of a vastly expanded set of basis elements. And so instead of using just a standard orthogonal basis, support vector machines use many basis elements. And it's called overcompleteness, and it's proving surprisingly successful in both regression and classification contexts. And I will note that this is absolutely alien to the way statisticians think, because we try and find very simple, sparse representations. And Vladimir Vapnik winds up with simple, sparse representations, but he gets there by first incredibly expanding the possible basis elements. Support vector machines have been developed in several different directions, and they've become quite elaborate. This survey is going to focus on linear machines trained on separable classes, just so we get the idea straight. Then we'll talk about linear machines trained on overlapping classes. And then finally, we'll talk about nonlinear machines. And the extension to more than two category classification can be done in the same way that linear discriminant analysis can be extended to more than two categories. But it's a little bit tricky, and you want to see Zhang and Liu's paper. Currently, support vector machines, random forests, and deep neural networks are the most successful of the sort of off-the-shelf classifiers. Deep neural networks take a long time to train compared with support vector machines and random forests. So as a practical matter, I encourage people to look at support vector machines and random forests as sort of their starting point. Suppose we have n observations in our training sample, where xi is a vector in RP and y is a label, and for now we're going to use the labels -1 and +1. And we seek a simple linear classification rule of this form. G of x is going to be the sign of beta transpose x plus beta naught, where the beta is going to be determined from the data, and it turns out that there's no loss of generality in saying that the norm of beta is equal to 1. If the two classes are separable, then there are many possible beta that work. And Vapnik's strategy is to pick the beta that creates the biggest margin between the two classes, the biggest separation. The margin is twice the perpendicular distance from the closest value with label +1 to the separating hyperflat, or the sum of the two distances from the +1 label to the -1 label surface. And this picture says it all. What you see right here are that the red points are all on this side, the green points are all on this side, and this blue point is a green point. These two blue points are from the red population, and they are called the support vectors because they determine everything there is to know about this yellow bar that separates the green side from the red side. Unlike discriminant analysis, unlike other types of statistical techniques, these red dots down here don't have any impact on the yellow margin. Some of these green points over here don't have any impact on the margin. It's just these three support points there that determine everything that's going on. And Vapnik's idea is to find the widest yellow strip that he can to determine the separating rule. So we'll define the margin by D, and the optimization problem is to maximize D subject to yi times beta transpose xi plus beta naught being greater than or equal to D. And since this has a sign -1, and if correctly classified, this will have a sign -1. So that's how he ensures that this product is always positive. And you can rewrite this as a convex optimization problem with a quadratic criterion in linear constraints. So we want to minimize beta subject to y transpose yi times beta transpose xi plus beta naught being greater than or equal to 1. And the requirement that beta have unit norm is no longer necessary. And it turns out that the margin D is 1 over the norm of the beta. And this solution is very different from the strategy that went into discriminant analysis. And in p dimensions, this solution depends only upon the p+1 closest points in the two classes. To solve it, you rewrite it as a Lagrangian, and you want to minimize L with respect to beta and beta naught, while simultaneously requiring that the Lagrange multipliers be non-negative. And the Lagrange formulation has two advantages. The original constraints are replaced by constraints on the Lagrange multipliers, and that's easier to handle. And the training data only appear once as dot products in this sum. And that is also going to be a nice feature that we're going to use later on. I'm not going to get too detailed about doing the Lagrange minimization, but you can reference it. The zero gradient requirement generates equality constraints, and so we wind up with this thing being what we're trying to solve. And this is maximized under the constraint that the lambda I yi equals 0 for all lambda I. The sum of the lambda i's is 0, and lambda I is always non-negative. What you find is that the Lagrange multipliers are 0 for all but p+1 of the yi's, and for and those determine what the support vectors are. So all the others are 0 except for the p+1 that determine the maximum margin surface, and that's how one does support vector machines when you have linearly separable classes. And I'll just jump back and make it clear. Here, we were able to perfectly separate the reds from the greens. The next case we're going to consider is linear machines, but the data are not separable. And in practice, it usually happens that they are not separable. And in that case, we do a slightly more athletic form of optimization that includes slack variables. And these can also be solved using Lagrange multipliers. And all of this is worked out in a paper by Cortez and Vapnik back some time ago. It turns out that this is equivalent to a problem in physics in which each of the support vectors exerts a force on a rigid sheet, and the equilibrium solution determines the separator. But a picture says it all. Here, these blue and red points are not separable. There is no margin that will put all the blues on one side and all the reds on the other side. But instead, we have these slack variables, these i's, and we want to minimize the amount of violation that the slack variables cause by stepping over the maximizing margin. So we're finding the maximizing margin, the maximum margin, subject to a requirement that there not be too many cases that violate the margin by too much. The interesting stuff are the nonlinear machines. And the mathematics of the support vector machine literature can be technical, but the key idea that underlies it all is to find linear combinations of basis functions of the x that give you good separating surfaces. And as noted in real problems, one wants more flexible separating surfaces than hyperflats. And Vapnik and others worked out how to do this. The main innovation is to express the surfaces in terms of a vastly expanded set of basis functions. So we map the support vector. So the support vector machine maps the problem to a high dimensional space. It finds a linear separator in that high dimensional space, and then it maps back down to the original space. And to see what's going on here, suppose we want to separate the red circles from the blue squares. Well, there is no linear separability here. There's no flat that I can draw that would separate them. But if I expand the set of basis functions to include terms of the form x minus a squared plus y minus b squared, then I can find a linear separator in this expanded space. And when I map it back down to the xy coordinate system, what I have is what was a linear separator in that high dimensional space becomes a circle in this low dimensional space. And so that's the strategy behind nonlinear support vector machines. If we're considering the problem of classifying just two types of objects, where each has measurements in RP, then one can find separating hyperplanes or quadratic surfaces, do linear or quadratic discriminant analysis, or we can fit more complex separating surfaces. And in principle, we would like to be able to fit pretty curvy surfaces when the data support it, and that can separate complex structure into two classes. And such surfaces can be formed by linear combinations of basis functions. And so you can imagine that some standard basis sets are the Fourier bases, the Legendre polynomials, the Hermite polynomials, and others. And a basis set is a set of functions f such that any function g in the space can be written as a linear combination of the basis elements, but no element of the basis set can be written as a combination of the other elements in that basis set. And what VAPDIC does is to have overcomplete basis sets, so that now elements of the basis set can be written in terms of linear combinations of other elements of that same basis set. And that's how he's able to do nonlinear separation by finding good basis elements. Consider expanding the set of inputs to include additional functions of the inputs. So, and we now have additional functions h1 of xi up to hq of xi, where if it's just the components of the original data, then q is equal to p, and we haven't expanded anything at all. But if we allow q to be greater than p, then we're adding in terms like x1 squared or x2 squared or x1 times x2 or other basis elements that might be useful. And now the separating surface has this form. In that higher dimensional space, we are looking to find a function g, which is a sum of coefficients times the dot products of the functions here, the functions of the inputs, plus an intercept. And formally, we often take an infinite dimensional Hilbert space as the expansion that we're considering. And we have a mapping H that takes the data from RP, the x1 to xp that we have, to this higher dimensional space. And one of the things we noticed in the optimization problem is that we can be written so it only depends upon dot products of the data, x transpose I times xj. And so after this new mapping H, it turns out that the optimization can be done only upon functions of the form h of xi transpose times h of xj. So it is sufficient to find this kernel function, which is going to be h of xi transpose times h of xj. And this means that we don't actually need to make the mapping H explicit, and that's called the kernel trick, since sometimes you only need to know the dot products. Determining the function in H turns out to be equivalent to selecting a basis for a particular subspace. And that depends upon a kernel function, and that's related to the reproducing kernel Hilbert spaces that I mentioned a while back. The kernel function is a semi-definite, positive semi-definite function. It's going to have this form. So it's going to be finding, it's a sum of the products of these vectors. And there are three common choices for the kernel functions in support vector machine applications. One is the radial basis kernel, and that has this form. And you'll note that it looks a lot like a normal distribution in here. You've got a distance squared. A second popular kernel are hyperbolic tangent kernels, and these look very much like a neural network basis. And finally, a third choice are the nth degree polynomials. And these aren't really as successful as the other two, but it's easier for us to talk about them. And I'll do an example with the nth degree polynomials in a moment. But for your work, the radial basis function kernel has been insanely successful across all sorts of applications. So if I were doing a problem for real, I would start off by trying a radial basis function and see how well that does for me. But to see how these ideas work, suppose that p equals 2, and we're using the nth degree polynomial basis with r equals 2. That means that our kernel function has got the 1 plus the dot product of x with x star squared. And we write that out. We see that we have terms of the form 1, 2x1, x1 star, 2x2, x2 star, x1, x1 star squared, etc. And thus, it turns out that we're now in a 6-dimensional space, and we can write the basis elements of that 6-dimensional space as h1 of x is 1, h2 of x is the square root of 2 times x1, h3 of x is the square root of 2 times x2, h4 is x1 squared, h5 is x2 squared, h6 is the cross product term. And so this means that the support vector machine is looking sort of for quadratic discriminating rules, and the programming problem is to find the best quadratic surface in terms of maximizing the margin in R6 that separates those classes. So that is the strategy for doing the support vector machines. I think I'm not really going to talk about the radial basis kernel much more. I will note that it is similar to the kernel regression estimator that we got with the Nadaraya-Watson approach back in the first hour of our lecture. So that's sort of the gist of support vector machines. Anything else I want to say here? No. I will emphasize that support vector machines do not automatically evade the curse of dimensionality. As p gets large, the second degree polynomial basis becomes very much like the multiple polynomial regression. And as we used in back when we were talking about the curse of dimensionality for the first time, I pointed out in high dimensions, the number of possible models explodes. And that's going to happen here with the second degree polynomial basis as p gets large. So there is no silver bullet. I'm hurrying a little bit because I want to get through random forests, which is the other standard competitor for support vector machines. And when they do bake-offs, what they typically see is that the recursive partitioning might be 1% better than support vector machines on one challenge problem and the other way around for a second challenge problem, but they almost always are head and shoulders above the third rank classifiers. Recursive partitioning is used for classification as well as regression. It's based on CART, and a classification tree in CART starts with a training sample of n cases with known categories, and case I has a vector of covariance x sub I, and then they build a tree-structured classification rule. So now we're not talking tree-structured regression. Instead, we're doing tree-structured classification. And this type of recursive partitioning is a very popular data analytics tool. So for classifiers, at each step, the algorithm considers 3 possible kinds of splits using the vector of explanatory variables x. It asks, is xi less than or equal to t? That would be a univariate split. It could do a linear combination split. Does the sum of wi times xi, is that less than t? And finally, it could do a categorical split if you have categorical data. It asks, is xi of a particular kind? So if you're trying to predict how long people will live based on, we might make a split on gender. That would be a categorical split. We might make a split on their blood pressure. Is their systolic blood pressure above 140 or not? Or you could do a linear combination split in which you might combine several measures of how fat or how skinny you are, some body mass index, subcutaneous fat measurements, something like that, into a single linear combination split. Classically, in Ryman, Friedman, Olson, and Stone, they used Gini's index of diversity, or they used a Turing rule. And so they're trying to find splits that will maximize the nodal purity after that split has been made. So in one case, they were trying to assign people as being people who had a heart attack or not. And this is a tool that was used by doctors when somebody may arrive at a hospital. And they ask, is the systolic blood pressure over the initial 24-hour period greater than 91? If not, over here. If it is, you go down here. Is the age greater than 62.5? If no, you go over here. If yes, you go down here. And then they ask, is sinus tachycardia present? And if it is, then you're here. If it's not, then you're over here. So this means that you probably aren't having a heart attack, but the G's means that you probably do. These classification trees are an ingredient to the random forest. A random forest is a collection of identically distributed trees. Each tree is constructed by the same tree classifying algorithm, and it might be CART or it could be one of the others. A random forest is formed by taking feed-forward samples from the training set. So what we're doing is we're collecting bootstrap samples from the training data, and for each bootstrap sample, we build a CART tree, and we do not prune the CART tree, we just let it keep growing until all the terminal nodes are pure, which means that you don't have members of different categories at the same terminal node. And at each split distribution, not all available covariates are considered. So unlike regular CART, where you look at all the possible splits and pick the best one, it turns out that random forest will only choose a random fraction of the variables. And that might be the square root of p of the variables, or it might be log p. So those are common choices. And that enables you to get a measure of the importance of each covariate as a function of the number of times it's chosen to be split upon. So if you're trying to predict how long somebody is going to live, and gender is terribly important in predicting that, well, it may be that the set of square root of p variables that you consider does not include gender. So the CART tree that's built from that is going to make some random choice and choose an inferior variable. But at the next stage, gender is part of it, and gender is selected. And if gender is always selected when it's available for selection, but not, then that means it's a terribly important variable. If gender is rarely selected when it's available for selection, that suggests that maybe gender is not so determinative of lifespan. And after the tree is grown, one drops a new case down each one of the trees in the forest, and the classification rule that receives the majority vote is the one that's assigned. And they were invented by Leo Breiman in 2001. And here's sort of an image of how it would go. We have a batch of trees, and we're going to be dropping things down. And over here, this might be class A. Here it winds up being class B. Here it winds up being class B. So the majority vote says this new case should be assigned to class B. There's some key features of random forests that are important to examine. One is it's a very, very good classifier. It's completely competitive with support vector machines, and in some ways, conceptually, I think a lot simpler. It provides its own internal unbiased estimate of the generalization error. And that is because it's called the out-of-bag estimate, or the OOB. And the way it works is when you are building a classification tree with a bootstrap sample, well, the bootstrap is sampled with replacement from the training data. And that means with a certain probability, a particular case is not used when building that CART tree. And in fact, it turns out that the probability that observation is not used in building a cart tree is about 1 over E as the sample size increases. Consequently, about a third of the trees in the forest do not use the first observation. So we can drop that first observation down those trees that were not part of, that did not use it in its construction, and you will see that, and you'll get an estimate of whether or not that first observation was correctly classified. Then you go to the second observation, you drop it down all the trees that did not use it to build the tree, and you can see whether or not it makes an error there. And so if we look over all of those observations and look at the error rate for the test sample, it turns out that we have an unbiased estimate of the generalization error. So that's a very cool property. Random forests handle missing data very well and contain high levels of accuracy when up to 80% of the data are missing at random. That's different from not missing at random, where it's informative missingness, and that's a problem. Random forest will provide estimates of the relative importance of each of the covariates in the classification rule. I already talked about that. That's because it doesn't look at all possible variables when it makes a split. It can measure proximities between pairs of cases that can be used in cluster analysis, and it can also be used to identify outliers in multidimensional scaling. And the idea there is, suppose we drop 2 cases down the same tree. If they wind up in the same terminal node, then they might be part of the same cluster. If they wind up in different terminal nodes, then they're less likely to be used in clustering analysis. Random forest can be used to do unsupervised clustering, and it can rebalance the weights when the category proportions in the training data do not reflect the category proportions in the true population. And that might arise, for example, if you're working for the IRS, the Internal Revenue Service, and you're trying to classify tax forms as being fraudulent or accurate. And so one imagines that the number of fraudulent forms is pretty small, maybe 1%. But you train the random forests with data that are 50% fraudulent and 50% honest. And then when you go out and use the random forest in the real world, you need to rebalance the weights so that the prior on the form that's being examined being fraudulent is 1% rather than 50%. There's an important warning, however, when using random forests. My former student, Tim Au, found a problem that he calls the missing labels problem. And that occurs when random forest makes a split, and beneath that split is a second split on a categorical variable. But in the training data used to construct that tree, not all of the labels for those categories are represented below that split. And as an example, one might try and make a split on gender and then on the US state in which you live. But if there are no women from Florida in the branch beneath that gender split, then you have the missing labels problem, and that can cause as much as 40% error in the final classification results. So you want to be very careful to avoid this missing labels problem. I think I'm going to talk a little bit more about bagging. Random forests are an extension of the idea of bagging trees, and that language is implicit in the out-of-bag estimator and things like that. Bagging refers to bootstrap aggregation, and it says that a way of improving the accuracy of a model is to start with a training sample, fit a model f hat to that, and now we want to predict the response for a new explanatory variable that we haven't seen before. And a bagged estimate for x star is found by drawing B bootstrap samples from the training data and using those B bootstrap samples to fit the models f hat 1 up to f hat b. And then the bagged prediction is going to be the average of all of those bootstrapped models. So that's a natural idea. If we are using trees for our f hats, then we can get random forests, but we could use other classifiers than trees. And here's a picture. Here, the error curves are a bagging example from the elements of statistical learning. And what it shows is that the test error of the original tree and the bagged tree is a function of the number of bootstrap samples. And what we see is that the Bayes rule is down here at the bottom. That's the best you can do. If we're bagging trees using either majority rule or voting, then we wind up doing very similarly here. And the original complex tree had how many? Just to say, okay. It was a very complicated tree, but it didn't perform very well. The bagging estimate is a simple average of models. Stacking builds on this idea by performing a weighted average where the weights often take account of the complexity of the models that are being fit. And so stacking can be viewed as a Bayesian version of model averaging, and the estimated weights correspond to Bayesian priors that probably would downweight complex models. So we imagine there are k possible models having different degrees of complexity, and the stacking prediction at a point x star has the form w sub k, a weight, times the bagged estimates, and then we do that weighted average, and that's going to give us the stacked value for x star. So each f hat k corresponds to one of the k models that we're considering, as fitted from the training data, and the weights are either based on complexity or estimated during the stacking. And I misspoke. The f hats do not use bootstrap sampling. They are built from very different types of predictors. So we might use a nearest neighbor model, a discriminant analysis model, a support vector machine classifier, and random forest model, and we put different weights on them according to whatever gives us the best predictive accuracy. In order to fit these, to predict x, we need to get these weights, and the weights are found by minimizing the sum of the squared discrepancies between the label yi and the fitted values obtained over here, where we are not using the ith observation in order to fit this f hat sub k. So that's going to put low weight on models that have bad leave one out accuracy in the training sample. But I remind you of the concern about the twin problem that occurs in cross-validation. If your data set are not IID, but instead have dependencies such that pairs of the data are very much alike, then this will be a problem. And one can use other methods in multiple linear regression to combine these models when finding the weights above. You might, for example, use a generalized additive model instead of this linear regression estimator to select the values for W. And I have 10 minutes left. Let me pause for a minute and ask, does anybody have any questions?
David, the messages that we are receiving are messages of Vinod said very nice presentation, and thank you, Dr. David. Alberto is saying great lecture. João is saying awesome lecture. So no questions, only words of thank and words of congratulations.
You guys are so nice. It's really delightful to be able to get that type of positive feedback, especially when I'm not able to be there in person and teach this. It's more fun when we're all in the same room together.
Yes, indeed.
Well, since I have 10 minutes and there are no questions, let me say a few words about boosting, because that sort of brings us to a natural end here. Boosting was invented by computer scientists to improve weak classification rules. So if one has a classification procedure that does only slightly better than chance at predicting the true categories, then one can apply boosting, and that will improve the classification rate. And it was originally proposed by Rob Shapiri, and then subsequently improved as a new algorithm that's called AdaBoost. And there are a number of refinements since, but the basic idea is pretty easy. Imagine that we have a binary classification problem. So the labels are 1 or -1, and we have a weak rule G1 of X. And AdaBoost starts by putting equal weight on each of the n cases in the training sample, and then the algorithm repeats the following steps k times. And k need not be very large, 50 would be fine. You apply the procedure G sub k, G sub 1 to start with, to the training sample with the weights that we started with, and then we find the empirical probability PW of misclassifying under those weightings. We calculate C sub k equals the natural log of 1 minus the probability of misclassification divided by the probability of misclassification. And if a case is misclassified, we replace the weight Wi by Wi times e to the C sub k. Then we renormalize so that the sum of all the weights is equal to 1, and we go back up to step 1. And we cycle through this about 50 times, 100 times. And at each case, we wind up getting this G sub k as the result. And the final inference is going to be the sum from k equals 1 to k of the weights C sub k times the classification rule G sub k. And that is going to be, that's boosted the initial weak classifier to something that should perform much better. And it has several impressive properties. It provably improves classification. It doesn't overfit, which arises when k is too large. The procedure allows for very quick computation, and it's practical even for very large data sets, and it's easily generalizable to handle more than 2 categories. Boosting provides an automatic and effective way to increase the capability of almost any classification technique. And initially, the theoretical justice for the empirical success of boosting was unknown. People suspected that it was maximizing the margin in sort of the way the support vector machines work, but nobody was sure. But then Hasty, Tibshirani, and Friedman wrote a paper in which they were able to link it to a formal loss function and develop theory that explains what the AdaBoost algorithm is doing. To illustrate the power of boosting, a graph on the next slide was constructed in the first edition of the Elements of Statistical Learning, and the graph shows the performance of a stump, which is a 2-node classification tree. So you have your first split, and then you have a second split. And this was compared to a 400-node classification tree and a boosted version of the stump. So the training data are 2,000 cases of xi in R10, and each component was drawn independently from a standard normal distribution, and the labels are assigned 1 or -1 according to whether or not the sum of the xi squared is greater than 9.34 or whether it's less than 9.34. And that's because the median of a chi-square distribution is 9.34. And what we see up here is that the single stump is terrible, the 400-node tree does this, and the boosted stump outperforms the 400-node tree. And so that's a really impressive improvement in the performance of the stump using AdaBoost. And for comparison, here we have a bagged decision rule, and here we have a boosted decision rule. And the boosted decision rule is doing better than the bagged decision rule for determining this separating surface. I will note that what boosting is doing is that it's upweighting the cases where it performed poorly and then refitting the classifier. And this technique is called forward stage-wise modeling. And in some sense, it's similar to Gaussian quadrature. You're trying to take the next point that will do the best job of predicting of explaining what hasn't been explained well before. Forward stage-wise modeling requires a loss function, and it turns out that boosting is using this loss function, e to the negative label for y, so this is negative the y value times the prediction from the rule. So f is a function that's going to give you either a positive number or a negative number. Y is a label that's either a positive 1 or negative 1. And it turns out that when they agree on the sign, then you get a positive number. E to the negative of a positive number tends to be small, so your loss function is very small. However, if y and f of x disagree on their sign, then their product is negative, and now we're taking e to a positive number, and that's going to give us a large value. So for this loss function, you pay a loss whether you're right or wrong, but you pay a really big loss when you're wrong, and only a small penalty when you're right. The forward stage-wise additive modeling algorithm starts the weak classifier G1, then it cycles through solving this thing, and then finally at the last step, it sets GK equal to GK minus 1 plus CK times GK. And I don't think trying to walk through math is very useful given the amount of time we have. If you go to HT Tibrani and Friedman, they'll explain how to solve these things and get the minimization that you need. They put it all in a package and show that the CK is going to be 1/2 the natural log of the inverse of the odds ratio. The error function is going to look as it is shown there. I guess the point I want to make is that boosting was not discovered with the exponential loss in mind. Shapiri just sort of followed his nose, did some stuff, and amazingly it worked. It wasn't until HT Tibrani and Friedman came along and really thought about this that the statistical justification for boosting became clear. And this feels to me like a very good place to stop the talk. I want to thank all of you for being part of this. I want to thank all of you for hanging in for 4 hours, and I hope you have a terrific evening. Thank you.
David, it was incredible. We are really very much thankful for it. We have here the comments that we have in the chat now are essentially comments of acknowledgement from Vinod. We have from Alberto, great lecture, from João, from Glacio, very nice lecture, Professor Banks, from Dr. Motija, the materials are very interesting, I am enjoying. From Mario Basto, thank you. So, David, thank you very much. It was really a very, very nice lecture, a very nice course. It was really, really great. We are really, really happy that you could make it and you could contribute to our conference. Thank you very much.
Thank you for inviting me, Paulo. It's a lot of fun, and it's always good to see you again. Take it easy.
Yes.
Have a great time.
Yes. Bye-bye. See you.
Bye.
Hope next time we'll be in person, right?
That would be terrific.
Yes. David, thank you very much. Thank you.
Thanks.